Imagine standing at the edge of a forest that stretches further than your eyes can reach. Trees as far as you can see, millions of them, some of them ancient, massive, centuries old. Now imagine every single one of them knocked flat, not randomly scattered, not tangled and chaotic the way a storm might leave them, all of them pointing in the same direction, like a giant hand reached down and swept them aside in a single motion. That's what investigators found in a remote corner of Siberia in the early 20th century. Roughly 80 million trees laid out in a radial pattern across more than 2,000 square kilometers of wilderness, pointing away from a single central point, like the spokes of a wheel, or like the ripple frozen in water after something enormous dropped into it. There's no crater, there's no obvious debris, there's no buried chunk of rock sitting at the center of the devastation. There's just the trees, silent, rotting, slowly being swallowed back into the earth, and the question they've been asking for over 100 years. What did this? That question sounds simple. It is not simple. In fact, it might be one of the strangest unsolved mysteries in the entire history of natural science, and the reason it's still unsolved isn't laziness or lack of effort. It's that the evidence keeps pointing in multiple directions at once. Every time researchers think they've locked down an answer, something else in the data pushes back. Think about the forces involved for a second. You need to flatten 80 million trees, not just knock them over, but release enough energy to do it almost instantaneously across a region the size of a major city. Scientists estimate the energy released at the equivalent of somewhere between 10 and 15 megatons of TNT. For comparison, the largest nuclear weapon ever detonated by the United States came in at around 15 megatons. Whatever happened over Siberia on the morning of June 30th, 1908, was essentially a nuclear-scale event. Except there were no nuclear weapons in 1908. There was no human technology on Earth capable of producing that kind of energy. So something came from somewhere else. But where? A meteor? A comet? A chunk of ice that vaporized completely before it even hit the ground? A natural hydrogen bomb triggered in the atmosphere? There are researchers who have spent their entire careers on this single event, and they still don't fully agree. The leading theories have shifted multiple times over the past century, and in recent years, new tools have allowed scientists to go back and look at the evidence in ways that simply weren't possible before. Some of those new findings have reopened debates that everyone thought were settled. That's what this is about. Not just what happened, but why we're still asking. We're going to walk through the evidence the way investigators did, starting with what the region looked like before the blast, moving through the moment itself, then following every trail researchers have chased since. The eyewitness accounts, the expeditions into terrain so remote it took decades for the first scientists to even reach the site, the microscopic particles pulled from soil and peat, the competing calculations about what kind of object could produce this specific pattern of destruction, and the nagging persistent problem that has quietly haunted this mystery from the very beginning. There is no crater. By the time we're done, you'll understand why this event, which happened more than a century ago in one of the most isolated places on the planet, still generates genuine scientific arguments today. You'll also probably be at least a little unsettled, because one of the threads we're going to follow is what would happen if the same thing occurred tomorrow, not over empty Siberian wilderness, but somewhere slightly less empty. Before we get into any of that, tell me where you are right now and what time it is there. I read these comments and it genuinely never stops being strange and wonderful. Someone's listening in the middle of the night in Cape Town. Someone else just woke up in Vancouver. Someone's on a train through Japan at 6 in the morning. If you're using this to fall asleep, that's exactly why I make them, so let me know. Drop your location and the time in the comments. Now, it's June of 1908, and we need to start where this story actually starts. Not at the explosion, but in the silence before it, in a stretch of Siberian wilderness so remote that the event it was about to witness would take nearly 2 decades to reach the outside world. To understand why this mystery took so long to unravel, you first have to understand where it happened. Not just geographically, but in terms of what that place actually was in 1908. Because the landscape itself is part of the story. Central Siberia in the early 20th century was about as close to the edge of the known world as you could get without falling off it. We're talking about a region larger than Western Europe, covered almost entirely by taiga, that vast, ancient forest of spruce and pine and larch that blankets the northern latitudes like a living ocean. In summer, it was boggy, insect-choked, and disorienting, a place where you could walk for days without seeing anything change. In winter it became something else entirely, temperatures dropping to 50 or 60 below zero, the silence so complete and so heavy it almost had a physical weight to it. The specific area we care about sits near the centre of this wilderness, a river called the stony Tunguska, or Podkamenia Tunguska in Russian, not to be confused with two other rivers nearby that share the Tunguska name. The stony Tunguska winds through one of the most isolated drainages in the entire country, surrounded by rolling hills thick with old-growth forest, interrupted occasionally by marshy clearings and the dark, slow-moving water of the river itself. There were no railways within hundreds of miles, no roads in any meaningful sense. Getting there meant weeks of travel by horse, by boat, by foot, depending on the season, and that's if you knew where you were going. The human presence in that region in 1908 was sparse almost beyond modern comprehension. The indigenous Evenki people had lived across this territory for centuries, semi-nomadic hunters and reindeer herders who moved through the taiga in small family groups, following animals, following seasons. Their population across the entire region was thin. Dozens of communities, sometimes separated by hundreds of miles of unbroken forest. Their knowledge of this land was intimate and deep, but their numbers were small, and they left no written records. There were also Russian settlers, mostly in the river towns and trading posts further out toward the edges of the region. Vanavara was the closest permanent settlement to what would become the centre of the event, and even Vanavara was tiny. A trading post, really. A handful of buildings on a riverbank where Evenki hunters brought furs and Russian traders exchanged goods. The population was in the dozens, 60, maybe 70 kilometres from the epicentre, and those were the close ones. This is exactly why the uncertainty around this event runs so deep. When something extraordinary happens in a place where almost nobody lives, the record it leaves behind is built almost entirely from the edges, from people who felt something strange happen from a long distance away, from travellers who passed through weeks or months later and heard second-hand accounts from people who'd been too frightened to approach whatever they'd seen. The closer you were to the blast, the less likely you were to leave a detailed written testimony. The further away you were, the more your account was filtered through distance and time. The Evenki oral accounts of what happened that morning are striking, and we'll get to them. But they existed in a world without newspapers, without telegraph stations, without any mechanism that would carry the story outward at speed. Word travelled the way everything travelled in that part of Siberia, slowly, on foot, by boat, through a chain of people each of whom knew a little less than the one before. This is how a nuclear-scale explosion in the wilderness of central Siberia generated barely a ripple in the world's awareness for years. There were distant observations, seismographs registering unusual readings across Europe and Asia, pressure waves detected by barographs in England, atmospheric disturbances that puzzled scientists at the time, strange glowing nights recorded across Russia and Europe in the days that followed. But nobody connected those threads to a specific place, because the place itself wasn't talking. When rumours did begin circulating, they were exactly that. Rumours, strange lights, a fire in the sky, trees knocked down somewhere deep in the Tunguska basin. The stories spread slowly through the trading networks, passed from Evenki hunters to Russian merchants to regional officials who had no particular reason to treat them as scientifically significant. This was 1908. People saw unusual things in the sky sometimes. Fires started in remote forests. It was remarkable, certainly. But remarkable things happened in Siberia, and Siberia was very far from anywhere that cared. The remoteness didn't just delay the discovery, it fundamentally shaped what kind of evidence survived and what kind didn't. No trained observers were anywhere near the site. No photographs were taken at the time of the event. No samples were collected in the critical hours and days afterward, when certain types of evidence would have been at their clearest. By the time the scientific world finally decided this was worth investigating, years had already passed, and the taiga had begun doing what the taiga always does, quietly absorbing everything back into itself. It would be nearly 2 decades before the first scientific expedition reached the stony Tunguska, and what they found there, standing at what should have been ground zero of one of the most violent events in recorded human history, would raise as many questions as it answered. So picture that silence, that vast, deep taiga silence of a June morning in 1908, June 30th. The sun already high by 4 in the morning at that latitude, the air cold enough to see your breath, the the forest just beginning to wake up with the sounds of birds and the distant movement of animals through the underbrush. For the Evenki families camped in the Tunguska basin, it started as an ordinary day, and then it stopped being one. The best reconstructions we have of the event's timeline come from a patchwork of sources, each capturing a different fragment of what happened. Witness testimonies collected years after the fact. Instrumental recordings made hundreds and even thousands of miles away. The physical evidence left in the landscape itself. Piece them together carefully and you get something like this. First came the light, not a flash, not a brief streak across the sky. Witnesses described something that appeared and grew, a second sun climbing over the horizon to the north and northwest, blue-white and overwhelming, bright enough to cast shadows at mid-morning, bright enough that people who saw it directly described temporary blindness, their vision bleached out for seconds or minutes afterward. Evenki herders camping near the river reported throwing themselves to the ground, convinced the sky was on fire. One man, Semenov, who was sitting on the porch of a trading post in Vanavara about 60 kilometers from the epicenter, described feeling sudden, intense heat on his face and his shirt nearly catching flame before a pressure wave threw him off his feet. He said it felt like someone had aimed a furnace directly at him from the sky. What he was experiencing was thermal radiation travelling at the speed of light, arriving well before the sound, well before the shock wave. The object was still in the sky when people started burning. Then came the shock wave, multiple waves actually. The initial compression front hit first, a wall of pressure that shattered windows, knocked people off their feet, threw reindeer off the ground and into the trees, toppled storage structures and sent birds erupting from every branch for miles around. People in Vanavara described being lifted and thrown. People further out described a sensation like being slapped by something enormous and invisible. And then, after a pause that must have felt terrifying in itself, the sound arrived. The booms were heard across an extraordinary range. Witnesses in towns more than 500 kilometers away reported hearing what they described as artillery fire, distant explosions, a series of thunderclaps that rolled on for minutes. In some places the sound arrived as a series of distinct blasts, in others as a continuous low roar. A train driver several hundred kilometers away stopped his locomotive because he thought something had exploded on the tracks. People in the city of Irkutsk, more than 900 kilometers distant, felt their windows rattle. Seismographs as far away as England recorded the ground vibrations. Barographs in London detected the pressure wave in the atmosphere not once but twice, the wave travelling around the entire planet and registering from both directions. That range of effect carries an important implication. The energy released in those seconds wasn't just locally violent, it was globally detectable. Scientists who've worked backward from the seismic data, pressure wave measurements, the size of the flattened zone, have estimated the explosion released energy equivalent to somewhere between 10 and 15 megatons of TNT. Some estimates go higher. For comparison, the bomb dropped on Hiroshima released roughly 15 kilotons. This was roughly 1,000 times more powerful, and it happened in the air, not on the ground. Now the eyewitness accounts. Here's where it gets complicated because those testimonies are both absolutely essential and deeply imperfect, and understanding why matters for understanding the whole story. The accounts were collected largely by a researcher named Leonid Kulik, who conducted interviews in the 1920s, roughly 15 to 20 years after the event. By that point, memory had done what memory always does, filled in gaps, smoothed rough edges, absorbed details from conversations with other people, layered later knowledge over earlier experience. Several witnesses described the object as a column of fire, others described it as a tube, others as a ball. Some said it moved silently until the explosion, others said it made a sound like the sky tearing. Some described one explosion, others described 3 or 4 or a long sequence of smaller detonations. These contradictions aren't evidence of dishonesty. They're evidence of exactly the kind of cognitive chaos that extreme, sudden, terrifying events produce in human observers. The object was moving. It was crossing the sky at an angle, which means different witnesses at different positions would see its trajectory differently. Some seeing it nearly head-on, some watching it streak across their field of view, some catching only its final seconds. The light was intense enough to distort perception, to make duration feel wrong, to make colour and shape blur into something that language can barely hold. And yet the common patterns across all those contradictory accounts are striking. Almost every witness who was within the right distance described the light coming first, then heat, then the physical force of the shockwave, then sound. That sequence isn't cultural, that's physics. It tells us the witnesses were genuinely describing something they experienced, not constructing a story after the fact. The consistent description of the approaching object as elongated rather than circular, visible for several seconds before the explosion, matches what we'd expect from something entering the atmosphere at an oblique angle rather than dropping straight down. The accounts of people and animals being knocked flat, of a hot wind rolling through the forest, of trees stripped of bark on the side facing the blast, these details repeat across independent sources with enough consistency to carry real weight. The furthest confirmed observations push the radius of noticeable effects to well over 1,000 kilometers. People in the town of Kirensk, roughly 400 kilometers away, saw what they described as a bright light moving across the sky. Passengers on a steamship on the Yenisei River, hundreds of kilometers to the west, felt the ship shudder. The atmospheric disturbance that followed produced something remarkable in the nights after the event. Strange, luminous clouds, bright enough to read by, spreading across Russia and into Western Europe for several nights afterward. People in England reported being able to see without lamps at midnight. Scientists noticed and wrote about it. Nobody yet knew what had caused it. Something had released an almost unimaginable amount of energy over the taiga that morning. Something that arrived as light and left as silence. And then the forest closed back over it, and the world moved on, and the question of what it actually was began its long, unresolved life. By 1908, humans had scattered barometers, seismographs, and other delicate instruments across the industrialized world like little mechanical ears and lungs, quietly listening to the planet. Most of the people who built and maintained them had never heard of the Tunguska River and never would. They were watching for storms, studying tides of air pressure, tracking subtle wobbles in the ground. What they ended up recording, without knowing it, was the fingerprint of an explosion in a forest they couldn't have pointed to on a map. Those barographs in London, for example, the same ones that registered the window-rattling pressure pulse from Siberia, didn't just spike once and call it a day. They showed a sharp, sudden jump in atmospheric pressure, then a slow return to normal. And then, hours later, another jump, and then another. What had happened is this. When the object over Tunguska exploded in the air, it shoved the atmosphere outward in all directions at once, sending a series of pressure waves racing around the globe. These waves behave a bit like ripples on a pond, except the pond is the entire atmosphere. The first wave reached Europe as a single crisp pulse, a sudden squeeze of the air followed by a rebound. Then the wave kept going, wrapped itself all the way around the planet and came back from the opposite direction, weaker but still measurable. In some barograph records you can see the atmosphere ringing like a bell, multiple passes, each smaller than the last as the disturbance slowly dissipates. At the time, this was a puzzle with no picture on the box. Weather services in Britain, Russia and elsewhere saw the traces but didn't know how to connect them. There was no global network where a scientist in London could instantly swap data with a meteorologist in St. Petersburg, compare notes, and conclude, these odd wiggles line up in time, they're coming from the same event. Telegraphs existed, of course, but the habit of treating atmospheric data as part of a planetary system was still in its infancy. So the barographs just quietly inked their lines on smoked paper, and the papers went into archives, waiting for someone decades later to realize they were all listening to the same moment. Seismographs told a similar story from the ground's point of view. The shockwave from the airburst didn't just hammer the forest and stop. It coupled into the ground, sending vibrations through the crust. Instruments designed to detect earthquakes in places like Irkutsk, Jena, Potsdam, even as far as Britain and possibly beyond, recorded small but sharp disturbances that didn't fit the pattern of ordinary tectonic events. The waves weren't coming from a fault line. They were coming from somewhere in central Siberia where, as far as anyone in Europe knew, nothing at all had happened. It was not until later, when Leonid Kulik and other researchers began piecing together the timeline, that these scattered squiggles of ink and tiny spikes on seismograms were reinterpreted as evidence of an enormous explosion in the atmosphere, an airburst whose mechanical violence was strong enough to jolt the crust and push the sky. This point is important because it solved one of the first major puzzles about Tunguska, how something could be powerful enough to flatten 2,000 square kilometers of forest, and still leave no obvious crater. If you only knew about craters, say, from seeing Barringer Crater in Arizona, or from reading about meteor strikes, you'd expect a hole. Big space rock hits ground, big crater appears. That's the mental model. Early on, some people assumed Tunguska must be the same. Maybe the crater just hadn't been found yet, hidden in a swamp, or masked by later growth. But the instrumental data pushed in a different direction. The pattern of the pressure waves, the timing and character of the seismic signals, the reports of multiple atmospheric pulses circling the planet, taken together, they suggested an explosion that happened miles above the surface, not at impact with it. In an airburst, the object, most likely a stony asteroid or icy comet fragment, doesn't survive intact to punch a hole in the ground. It slams into the atmosphere at tens of kilometers per second, compressing the air in front of it until the pressure and heat become intolerable even for rock. At some critical altitude, the object breaks apart violently, converting its kinetic energy into heat, light, and a shock wave. The forest underneath experiences devastation comparable to that of a ground-level nuclear blast. But the Earth itself never receives a solid impact. No crater, just a blast. That idea, that you could have a planetary-scale explosion without a crater, was not obvious in 1908. It only became plausible when scientists revisited the barograph traces and seismograms and realized they matched what you'd expect from a massive atmospheric detonation. Combined with the radial pattern of flattened trees that would be mapped years later, they pointed to a detonation height on the order of 5 to 10 kilometers above the surface, high enough to spare the ground from a direct blow, low enough to obliterate everything standing beneath. But the planet didn't just feel Tunguska in pressure and tremors, it saw it too. In the nights following June 30th, people from Western Russia to Scandinavia to the British Isles began reporting something strange in the sky. The nights were wrong, too bright. Newspapers in London, for instance, carried stories about remarkable luminous nights. People wrote letters describing midnight streets where you could read a newspaper without any artificial light. Golfers claimed they could play late into the night and still see the ball. Observers in Scotland, Germany, and across northern Europe noted bizarre silver-white clouds that glowed after sunset, rippled forms high in the sky that shone with an eerie electric sheen. These weren't auroras. They appeared too far south, and their colour and structure were different. Contemporary scientists struggled to explain them. Some thought they might be linked to volcanic dust, because similar afterglow skies had been recorded after major eruptions like Krakatoa in 1883, when ash and sulfuric aerosols injected high into the atmosphere created spectacular sunsets and prolonged twilight for months. But no big eruption had been reported. Today, most researchers see those luminous nights as part of the same story as the flattened forest and the barograph spikes. When the Tunguska object exploded, it didn't just release energy, it injected material into the atmosphere. Tiny particles of dust, smoke, and vapour from the disintegrating object and from the forest it instantly incinerated would have been lofted high into the upper layers of the atmosphere where winds can carry them across continents. Up there, in the mesosphere, conditions are cold and thin enough that water vapour can condense onto tiny particles and form ice crystals. Under the right conditions, those crystals form what we now call noctilucent clouds, night-shining clouds, visible only when the sun is below the horizon, illuminating them from below against a dark sky. The strange silver veils seen over Europe in the days after Tunguska look very much like intense outbreaks of noctilucent clouds, possibly enhanced by a sudden injection of dust and water vapour into the high atmosphere. If that interpretation is right, then the luminous nights are telling us something about the altitude and composition of the debris cloud. To light up the sky over London, the particles had to be lifted extremely high, tens of kilometres above the surface, and spread along the high-latitude atmospheric circulation patterns that encircle the pole. Their brightness suggests not just soot from forest fires, but also fine particulate matter, efficient at scattering sunlight, perhaps mineral dust from the object itself or condensed droplets of water and other volatiles. All of this, the barograph ringing, the seismic shudder, the night-shining skies, paints a picture of Tunguska as not merely a local catastrophe, but a planetary event. A forest falls in Siberia, and the air itself hums in London. A flash of light over the Tiger, and nights half a world away turn electric. And yet, for all that, our view is still blurry, because the world of 1908 didn't have the kind of global sensor net we take for granted now. No weather satellites tracking the expansion of the dust plume, no global network of GPS-based sensors timing the arrival of atmospheric waves to the second, no coordinated seismic arrays designed to triangulate explosions. Data existed, but it was patchy, local, and often collected for entirely different purposes. Barographs were run by national weather services interested mainly in storms. Seismographs were tuned for earthquakes. Observers in Europe and Asia wrote about strange skies, but their reports went into newspapers, not a centralized scientific database. Many instruments in Asia, closer to the event, were sparse or poorly archived. Telegraph lines could carry news quickly, but only if someone recognized a pattern worth reporting. Because of that, later researchers had to reconstruct the global impact of Tunguska from fragments. A barogram here, a seismogram there, a newspaper clipping, a diary entry about midnight brightness. Aligning these scraps in time and space, allowing for errors in clocks and distances, has always involved interpretation. Change your assumptions slightly about when exactly the explosion happened, or how fast the atmospheric waves travelled in that season's conditions, and your reconstruction shifts. Some scientists emphasize the consistency. Independent instruments, thousands of kilometers apart, all recording disturbances that converge around the morning of June 30th. Others point to the uncertainties, incomplete coverage, possible miscalibrations, human error in reading analog traces. Different weight given to different sources leads to different estimates of the explosion's energy, height, and orientation. That's one reason why modern estimates of Tunguska's yield still span a range of several megatons. So when we talk about Tunguska as an enormous airburst inferred from global data, we're really talking about a kind of forensic science conducted across time. Nobody in 1908 saw the whole event in real time. No single instrument captured the explosion and neatly labelled it. Instead, the planet reacted, air shaken, ground shivered, sky glowed, and decades later, scientists looked back and realized all those reactions pointed to the same invisible hammer blow over Siberia. And if the instruments and the sky were telling one part of the story, the forest itself was telling another. Because on the ground, beneath that invisible blast, 80 million trees didn't just fall, they fell in a pattern. And that pattern turned out to be one of the clearest and strangest clues we have. When Leonid Kulik finally forced his way into the Tunguska zone in the late 1920s, that pattern was what hit him first. Not a crater, not a blackened pit, just trees, everywhere, lying on the ground like someone had combed the forest flat with an invisible rake. Imagine walking into a landscape where the trees are no longer vertical elements but lines on a page. Larches, pines, birches, all snapped off or uprooted, trunks pointing away from a roughly central region like the spokes of a gigantic wooden wheel. For kilometers in every direction, the taiga had been pressed down, not randomly, but radially, everything pointing outward, as if the forest itself were an explosion diagram drawn in living wood. This wasn't what most people had imagined. Early rumours talked about a meteorite fall, and Kulik himself had gone in expecting something like Barringer Crater in Arizona. A big hole, a raised rim, maybe shards of space rock scattered nearby. Instead, what he found looked more like the aftermath of a god-sized hand slamming down on the canopy and sweeping outward. And the pattern wasn't uniform. The more carefully he and later investigators mapped the fallen trunks, the stranger the geometry became. If you trace the directions of treefall, literally follow the direction each trunk is pointing, you can reconstruct the flow of the shockwave. Near the outer edges of the damaged zone, the trees all lean, or lie down facing away from the centre, their tops pointing outward, roots often still in the ground but tilted. Closer in, many are snapped at mid-height, blown over like matchsticks, with splintered stumps still in place. The directions converge back toward a central area where something different happened. In that core, roughly a few kilometres across, investigators did not find trees pointing outward at all. They found trees still standing, not intact, not healthy. Their branches were stripped, their bark scorched, their upper sections sometimes broken off. But the trunks themselves, especially the thicker ones, remained vertical, blackened poles rising out of a sea of flattened timber. This eerie stand of telegraph poles, as some witnesses later called similar scenes, was one of the key surprises of the Tunguska blast. If the explosion had been caused by something hitting the ground, You might expect the closest trees to be bulldozed in toward a crater, or shredded in chaotic directions by ejecta. Instead, the nearer you got to the point below the airburst, the less the trunks were knocked sideways and the more they were simply roasted and stripped. It suggested the main blast had come from above, not from the ground. The strongest overpressure was directed downward and then outward as a radial shock front racing just above the surface. In other words, the forest had become a recording surface. The trees were like thousands of arrows frozen in place at the instant the shockwave passed, each one indicating the direction the air was moving when it hit. Map enough of them, and you get a kind of fossilized pressure field. That's exactly what researchers did. Over several expeditions, Soviet teams fanned out across the damaged region with compasses and notebooks, measuring the orientation of fallen trunks, classifying burn damage, sketching local patterns. When they plotted this information on a large-scale map, a distinctive shape emerged. From above, the devastation didn't form a perfect disk. It formed something more like a stretched oval, with two major lobes fanning outward from the epicentral area, what later authors started calling a butterfly pattern. In simple models, you might expect an airburst to generate a roughly circular zone of damage. Energy radiates equally in all horizontal directions. Trees fall away from the center, end of story. But Tunguska wasn't simple. The object that exploded was moving fast, tens of kilometers per second, along a particular trajectory through the atmosphere. When it broke apart, the energy didn't just explode in a stationary sphere, it was smeared along its path and directed preferentially forward and sideways. Think of a bomb going off while it's still moving. Part of the shock is centered near the breakup point, but debris and energy continue along the original trajectory for some distance, generating an elongated region of high overpressure. The resulting blast footprint on the ground can end up stretched along the path, with lobes of heavier damage downrange. Combine that with atmospheric layering, reflection of shock waves from the ground, and the angle at which the object came in, and you get a pattern that looks less like a neat donut and more like a pair of overlapping fans. Some reconstructions suggest that Tunguska's butterfly aligns with the trajectory from the east-southeast toward the west-northwest. Others, using different witness reports and later numerical models, argue for a steeper angle from the south, or a more shallow one from the east. The exact path is still debated, partly because the mapping of treefall directions was done decades after the event, in a forest that had already begun to regrow. But the general principle is solid. An angled incoming body that explodes in the air will tend to create an asymmetric damage pattern. More trees will fall in the directions where the moving shock front had the highest momentum and where the air column focused the blast. The butterfly wings on the Tunguska map are forensic evidence for that angled trajectory, even if they can't by themselves tell you the precise entry angle to the nearest degree. This is where treefall becomes less just destruction and more like a diagnostic tool. In modern blast investigations, whether from accidental explosions, weapons tests, or volcanic blasts, analysts use fallen objects as vector arrows. Walls blown outward, trees toppled, debris scattered. Each piece points away from the pressure source. If you have enough vectors, you can triangulate back to where and how the energy was released. In Tunguska's case, the forest was the debris field. The radial lay of the trunk said, the main impulse came from roughly here, at this altitude, with this general direction of travel. The standing, scorched trunks in the center said, the closest trees were hit from almost directly above, with such intensity that their crowns and branches were obliterated, but their thicker lower trunks didn't have time to bend before being stripped. Even the height of the airburst can be constrained, roughly, by how far out trees were flattened, how much pressure it would have taken to knock them down, and how quickly the shock would have decayed with distance from a point in the sky. Combine that with the absence of an impact crater, and with the global pressure wave data, and you start converging on an explosion perhaps 5 to 10 kilometers up, releasing on the order of several megatons of energy. But the trees were also burned, and those burn patterns carry their own clues. Witnesses on the periphery spoke of a fire on the horizon, a glow, a column of light. In the central zone, many trunks were stripped of branches and bark, with the wood beneath charred or baked. Yet the forest did not become a continuous, raging inferno that consumed everything in its path for weeks. Patches burned intensely. Other areas, even within the flattened zone, showed little sign of deep charring. This is important. A nuclear surface blast, for instance, produces not only a blast wave but also an intense thermal pulse that can ignite flammable materials over a broad area almost simultaneously. You'd expect large-scale crown fires, sustained burning, and a very different pattern of char. Tunguska's burn signatures look more like what you'd get from a brief but enormous flash of radiant heat, followed by secondary fires in places where dry material, resin, and perhaps human ignition sources were present. Lightning, campfires, whatever happened to be there. The standing, scorched trunks near ground zero tell a specific story. The thermal radiation was intense and short-lived, strong enough to blister and carbonize exposed surfaces on the side facing the blast, to strip needles and leaves off conifers, to ignite some materials, but not long enough to deeply burn thick wood everywhere, or to sustain a firestorm that travelled far beyond the blast zone. Some parts of the bark show evidence of having been superheated and then rapidly cooled, consistent with a bright, brief heat pulse from a high-altitude explosion, rather than hours of exposure to lower-intensity flames. At greater distances, char is more selective. Exposed, resin-rich surfaces, dry undergrowth, and certain tree species show more damage than others. In swampy or wetter areas, trees may be blown down without significant burning at all. That patchiness fits a scenario in which the initial flash lit many small fires that either sputtered out or merged into localized burns, heavily influenced by microclimate, fuel moisture, and wind after the blast. So the burn patterns support the airburst interpretation and argue against scenarios involving large amounts of ground-level molten material, extended lava flows, or sustained volcanic-style eruptions. They are also hard to reconcile with some of the more exotic suggestions that have cropped up over the years, like massive chemical explosions or secret early nuclear tests, because those would leave different signatures in both damaged geometry and fire behavior. Still, there are hard limits to what you can deduce from trees alone. Treefall directions can tell you where the pressure was strongest and broadly which way the energy moved, but they can't tell you the object's exact speed, mass, or composition. A stony asteroid and an icy comet fragment of similar size and trajectory could produce very similar blast patterns in the forest. The trunks don't care what blew them over, they only record the mechanical result. Burn patterns can tell you that there was a powerful flash of thermal radiation and where it was strongest, but they can't reveal whether that heat came from incandescent rock fragments, a plasma fireball, or a chemically unusual explosion without additional chemical and mineralogical evidence. The trees don't preserve isotopes. They don't archive the microscopic spherules or weird mineral phases that might distinguish one kind of cosmic intruder from another. Even the butterfly pattern, as striking as it is not a perfect photograph of the original shockwave. Wind after the event, rot, later fires, and simple human error in mapping can all blur the picture. Early expeditions didn't cover every square kilometre. Some directions were estimated, some trees misclassified. Numerical simulations can fit more than one plausible trajectory to the same imperfect data. In that sense, the Tunguska forest is like a witness with a phenomenal memory of where they fell, but no idea what hit them. The trees show us that the blast came from above, came fast and came along a particular line of travel. They tell us it was violent enough to flatten 80 million of them in seconds, and hot enough to scorch bark and ignite scattered fires across 2,000 square kilometres. They sketch, in wood and charcoal, the outline of a megaton-scale airburst. But they stop there. Beyond that outline, if you want to know what actually tore itself apart in the sky above the stony Tunguska River, you have to look for other kinds of evidence, in other parts of the landscape, and even in the chemistry of the soil and the air. The forest provides the map. The next question is whether that map leads to a missing crater, or to something stranger. For almost 20 years after the sky exploded, that map in the trees was just sitting there, waiting, and nobody with the tools to really read it came. Part of that was politics, part of it was geography, and part of it was that Tunguska happened in the worst possible place if you want quick, neat answers. In 1908, the Russian Empire had other problems. A revolution in 1905, war with Japan, unrest simmering everywhere. A report about a bright flash and a distant explosion in some barely mapped corner of Siberia was interesting, but it wasn't exactly top of the agenda in St. Petersburg. A few newspapers ran stories. A few scientists noted the seismic and barometric data and shrugged. Probably a meteorite. Somebody should go look someday. Then the First World War began, then the Russian Revolution, then the Civil War. By the time the dust settled and the new Soviet state was in any position to fund scientific expeditions, a decade and a half had passed. The trees were already starting to rot. New growth was creeping in. Witnesses were aging or moving away. The event that had made the whole planet ring like a bell was slipping out of living memory. Into that gap stepped Leonid Kulik. Kulik was not the stereotype of a glamorous explorer. He was a former soldier, a self-taught meteorite obsessive, a man who had spent years cataloguing small lumps of space rock in museum drawers. But he had something that mattered more than charisma, an almost fanatical belief that Tunguska had dropped a meteorite worth finding. To him, the idea that such a colossal explosion didn't leave a big chunk of iron or stone buried in the ground wasn't even on the table at first. When he looked at the barometric traces, the eyewitness reports, the accounts of a fireball in the sky, his brain did what everyone's brain had done for centuries. Big fire in the sky plus big bang equals big rock. So when he finally convinced the Soviet Academy to back an expedition in the late 1920s, the mission was shaped by that assumption. This was a treasure hunt. Somewhere out there, he thought, lay a meteorite that might be massive, valuable, scientifically priceless, maybe even a cluster of them. The job was to haul them back. There was just one problem: getting there. On a map, the Tunguska region is just some rivers and some green shading. On the ground, it is an obstacle course designed by someone who hates wheels and loves mosquitoes. The stony Tunguska basin isn't just remote in the sense of being far away. It's remote in the sense of having almost no infrastructure, no proper roads, and a landscape that actively resists movement. Between the last railhead and the blast zone, Kulik's team had to cross a patchwork of swamps and taiga that swallowed carts and horses alike. Spring melt turned low ground into lakes of black, sucking mud. Rivers ran high and cold, braided into channels that shifted year to year. Bridges didn't exist. You built your crossing, or you didn't cross. The forest itself wasn't the neat park-like woodland most people picture. It was dense stands of larch and pine, tangles of undergrowth, fallen logs hidden beneath moss, clouds of midges and mosquitoes thick enough to form a moving fog around every human body. In that environment, you don't casually drag heavy equipment around. Every kilogram hurts. Kulik's party travelled by train, then riverboat, then horse, then on foot. Supplies had to be ferried in stages. Illness was common, insects were constant. The idea of doing a clean, gridded survey of a 2,000 square kilometre blast zone in those conditions was fantasy. They were improvising every step. This is where local knowledge became the difference between reaching Tunguska and just dying somewhere east of nowhere. Indigenous Evenki and other local people had been living in that landscape for generations. They knew which river channels were passable in which season, which bogs could be skirted, where the ground rose enough to camp without waking up underwater. They read subtle signs in the forest, tree species, soil colour, animal tracks, that told them which way to go when the map was just a blank. Kulik needed that knowledge. He needed guides who could translate a line on a crude sketch into 3 days of actual walking. But the relationship wasn't simple. For the Evenki, the place where the blast had happened was not just a study area. It was charged with meaning. Many accounts say they avoided the epicentral region, calling it cursed or dangerous. Their stories talked about a god or spirit angry with the people. The explosion wasn't a scientific event, it was an event in a moral universe. So you had this uneasy intersection. On one side, a scientist with a mental picture of a big rock in the ground, convinced that the answers were physical, measurable, repeatable. On the other, guides whose understanding of the event was woven into tradition, taboo, and memory, and who were not particularly eager to march straight into the heart of what they saw as a supernatural disaster zone. That tension shaped every decision: where to camp, which route to take, how long to stay. The result is that Kulik's expeditions moved through a landscape already filtered by indigenous choices, paths that avoided certain places, routes that favoured high, dry ground over swampy lowlands. In a very literal sense, indigenous knowledge determined which parts of Tunguska science even got to see first. When they did finally push into the devastated region in 1927 and the years after, Kulik's expectations came with them like extra baggage. He expected to find a crater, so he saw the landscape through that lens. A depression here, maybe the impact site, an area where trees were more broken, perhaps closer to ground zero, Strange swampy hollows, possibly filled in craters. He photographed, sketched, measured, but always with the thought that somewhere nearby, just beyond the next ridge, the classic meteorite signature was waiting. He even thought he might find smaller craters clustered around a big one, pieces that had broken off before impact. Many meteorite falls we know leave that kind of pattern. Multiple pits, fragments scattered downrange. He looked for that. Local stories didn't necessarily help. Some described holes or lakes that had appeared or changed after the blast. But in a swampy region where lakes and ponds come and go with permafrost thaw and river shifts, that kind of description is frustratingly nonspecific. Is this pool new, or just new to the person telling the story? Did the explosion make it, or did people start noticing it because of the explosion? Still, guided by those accounts, and by his belief that a massive body had hit, Kulik focused his efforts on low-lying, wet areas that could plausibly hide a crater under water and muck. He made plans to drain a certain suspect bog. He was constantly scanning the horizon for a raised rim, a ring of ejecta, anything that matched the mental template of a classic impact site. It never appeared. He climbed hills and saw nothing but flat, endless taiga and that eerie ring of flattened forest. He waded swamps and found peat, water and rot, but no buried iron. He walked kilometre after kilometre across a landscape that screamed blast in its tree patterns, but refused to cough up a single obvious chunk of meteorite. The more he looked, the stranger it became. Everything pointed to a central point in the sky. Nothing pointed to a hole in the ground. In a way, the forest was arguing with him. The radial treefall said, the energy came from above, then spread outward. The standing, scorched trunks in the centre said, nothing ploughed through here. The worst of it hit from directly overhead and then passed on. The absence of any raised rim, any disturbed stratigraphy on a large scale, any clear ejecta blanket said, whatever exploded, it did not punch into the earth like a bullet. Kulik didn't immediately accept the full implications of that. His early reports still talk about the likelihood of a buried meteorite, of bodies that had penetrated more deeply and might be located with better tools. He floated ideas about a fragile or icy meteor that had shattered, about fragments that might be small or widely scattered. The hypothesis bent and twisted to accommodate the missing crater, but he didn't drop the basic assumption that something solid had hit. It's easy, in hindsight, to say he should have. Now we're comfortable with the idea of airbursts, objects that never reach the ground intact, that disintegrate high in the atmosphere and convert their kinetic energy into a blast wave and thermal radiation alone. We've seen Chelyabinsk. We've modelled these things on supercomputers. Kulik had none of that. For him, the idea of a 50 or 60 metre object completely vaporising in midair without leaving a neat crater was radical, unintuitive. You can almost feel him wrestling with the data, trees pointing outward, witnesses describing a fireball that never touches the ground, no crater, and yet an energy release comparable to the biggest explosives humans could then imagine. That tug of war between expectation and evidence is what turned the missing crater from an inconvenience into the central mystery of Tunguska. If you find a crater, the story is relatively simple. Measure the hole, calculate the energy, collect the meteorites, write the paper. But if you don't, then what? Kulik's meticulous but craterless surveys forced scientists to confront that question. By ruling out the obvious, a classic impact bowl with big chunks of rock, his expeditions made the absence itself into data. The lack of a crater, in combination with the treefall map and the global shockwave records, was not just a missing piece, it was a clue. It meant the energy had to be released at altitude, over a wide area with almost nothing solid reaching the ground at high speed. It meant whatever object came in had to be fragile enough, or volatile enough, to be destroyed by atmospheric stresses and heating before it could dig its own grave. From that point on, any explanation of Tunguska had to start with that void. Not with what was there, but with what famously wasn't. Kulik went into the silence of the flattened forest looking for a hole in the earth. What he actually found was worse, from a certain psychological point of view. A perfectly intact surface beneath a sky that had once, for a few blinding seconds, behaved like a weapon of the gods. That empty ground is what future investigators would keep circling around. If there was no crater, they asked, then what on Earth, or beyond Earth, could flatten 80 million trees and leave almost nothing solid behind? If you take a big rock from space and slam it into a planet, the usual outcome is not subtle. A classic impact crater has a shape that geologists can practically recognize from orbit at a glance. There's the circular depression, the raised rim, the blanket of ejecta flung outward in a thinning sheet of debris. For really big hits, there's often a central uplift, a rebound peak where the ground, slammed down and then elastically bouncing back, pushes a knob of rock up in the middle like a frozen splash. On Earth, erosion, vegetation, and human activity can blur the edges, but the bones of that structure usually remain. You can bulldoze the sides, you can fill the bowl with sediment. The rim and the disrupted layers underneath are still there if you dig or scan deeply enough. Rock is hard to erase, so when scientists in the mid-20th century said Tunguska was a huge impact, their mental picture wasn't mysterious at all. Of course there should be a crater. The only debates were about how big it ought to be and what kind of meteorite lay inside. Here's the strange thing. We've looked. Not just Kulik with his boots and bayonet probes, but generations after him with aerial photography, satellite imagery, magnetometers, seismic surveys, even LiDAR. And in that 2,000 square kilometre zone of flattened forest, there is no obvious, textbook impact crater. Nothing on the scale of the energy release, nothing that matches the circular bowl, the uplifted rim, the pattern of excavated rock you'd expect from an object dumping tens of megatons of energy into the ground. Instead, you have that radial pattern in the trees, the burned strip of epicenter, a few small ponds and boggy depressions that have each taken their turn as, maybe this is it, and then disappointment. Peat, permafrost, normal sediments, but not the deep pulverized glassy mix of shocked earth and melted impactor that screams, something hit here at cosmic speed. So either Tunguska was not a typical impact, or the crater is hiding in ways that typical craters do not. To understand how we got from "where's the hole" to maybe there never was one, you have to climb upwards, off the ground, into the air the object never managed to leave. When a space rock plunges into Earth's atmosphere, it's not falling through empty space. It's ramming into a gas that, at orbital velocities, might as well be a fluid wall. The faster and bigger the object, the more brutally that wall pushes back. At 20 kilometers per second, a reasonable speed for a cometary fragment, each square centimetre of leading surface is hitting air with unimaginable force. That pressure, combined with frictional heating, starts stripping material from the body. It ablates, like an ice cube in a blowtorch. If the object is solid metal, it can plough through that punishment and reach the ground more or less intact. If it's stony, fractured, or full of volatile ices, it has a much harder time. Think of it less like a cannonball and more like a frozen, loosely packed snowball hurled at a brick wall at Mach 60. The outside compresses and heats. The interior is still cold, still weak. Stress builds. Cracks propagate faster than sound can carry the news. Somewhere between 5 and 15 kilometers above the ground, the whole structure can reach a point where it simply can't hold together. And then it fails. That failure isn't a gentle breaking apart, it's an explosion. All that kinetic energy that was being carried forward in one compact lump suddenly gets dumped into the surrounding air as a massive blast wave and a flash of thermal radiation. This is an airburst. We've seen smaller versions. The Chelyabinsk event in 2013, caused by an object about 20 meters across, exploded around 30 kilometers up. It never hit the ground as a whole. Yet the shockwave shattered windows across a city, injured more than 1,000 people, and was recorded around the world by infrasound stations as far away as Antarctica. Scale that up, make the object perhaps 50 to 80 meters wide, denser, and let it penetrate deeper into the atmosphere before it disintegrates. Drop the blast height from 30 kilometers to maybe 8, 10, 12. You don't get a neat hole, you get a sky-sourced hammer. The reason an airburst can rival a ground impact in destructiveness is simple physics. Energy has to go somewhere. Whether it couples to rock or air, the numbers don't just vanish. If the explosion happens high, that energy goes into compressing and heating a vast volume of atmosphere. That compressed bubble then rushes outward as a shock wave, curving down and sweeping across the surface like an invisible tsunami. By the time it hits the ground, the front of that wave can still be moving at hundreds of meters per second. The overpressure, the extra force above normal atmospheric pressure, is enough to snap trees like twigs, knock people off their feet, collapse flimsy structures. The thermal pulse that accompanies the blast can ignite fires, singe bark, and scorch the facing sides of objects without the need for any molten rock or raining debris. It's the same basic mechanism as a nuclear airburst minus the radiation. In fact, a lot of early modelling of Tunguska borrowed tools from nuclear weapons research, because at that scale and altitude, the physics of blast propagation is strikingly similar. Now, go back to that eerie central zone Kulik described, the place where trees were not flattened but left standing, stripped of branches, charred on one side. To early investigators, that looked almost like a contradiction. If this was ground zero, why weren't the trees blown outward from the middle? Why were there more upright trunks so close to the supposed epicenter than farther out? This is where blast dynamics get counterintuitive. When an explosion occurs above the ground, the shock front expands spherically at first, then begins to interact with the surface. There's a region directly underneath where the flow is mostly downward at first, then outward along the ground. Farther out, the wave slams in at a shallower angle, more horizontally. Imagine standing under a giant speaker. Right below it, the sound pushes mostly down on your head and shoulders. A few meters away, the pressure has room to spread and hits more from the side. Same energy, different geometry. Tunguska's trees recorded that geometry. Very close to the point directly under the airburst, the dominant force seems to have been downward and somewhat chaotic. Branches blast-stripped, bark scorched, trunks damaged but not all toppled in a neat radial pattern. As you move outwards, the shock front that has curved and reflected off the ground arrives as a more horizontal shove. There, the trees lie flat, pointing away from the epicenter, like metallic filings lining up in a magnetic field. That inner standing forest is not a sign that nothing happened there. It's a sign that something different happened there. Extreme thermal and vertical loading without the same lateral sweep that did the lumberjack's work farther out. If a big solid object had actually slammed into the ground at that central point, the pattern should be different. You'd expect a blast that originates at or just below the surface, with uprooting and radial blowdown extending through the epicenter itself. The central trunks wouldn't be spared. They'd be the first casualties. Instead, Tunguska looks like an invisible hand pressed straight down from above, then flung its fingers outward as it spread. The absence of a crater and the peculiar behavior of those central trees are not independent puzzles. They are two sides of the same answer. The energy release was in the air, not the ground. But human curiosity being what it is, people have not been content to stop there. If there's no obvious crater, could it be hiding? Could it have formed and then vanished? Or are we wrong to expect a crater at all? One camp has argued for a hidden crater, buried under peat and lake water. The favourite candidate for years was Lake Checo, a small, almost circular body of water a few kilometres northwest of the estimated blast epicenter. Some studies claimed its sediments seemed too young, that its shape and depth profile looked suspiciously like an impact bowl filled with water. Other researchers pushed back. The lake seems to rest comfortably in undisturbed layers older than 1908. Its morphology matches that of normal thermokarst lakes formed by melting permafrost. Seismic and core samples don't show the chaotic mixed sediments or shocked minerals you'd expect from a fresh impact. Lake Checo, if it is a crater at all, is a very strange one, and the evidence mostly says it isn't. Another idea is the vanished crater hypothesis. In a wet, boggy, permafrost-dominated landscape, could an impact pit simply slump, fill, and disappear within a century? Erosion on Earth can be fast, but not usually that fast for structures hundreds of meters across and dozens deep. Known terrestrial impact craters millions of years old are still recognizable. Even heavily eroded ones leave geophysical fingerprints in shattered bedrock, impact melt, and magnetic anomalies. If Tunguska carved a hole big enough to match the blast energy, something of that violence should remain under the moss. So far, detailed surveys have not found such signatures scaled to a large crater, which brings us back to the most straightforward, if unsatisfying, possibility. There is no crater because the object never got the chance to make one. In that scenario, Tunguska was essentially all airburst. A fragile, probably icy or loosely consolidated body came in at a shallow angle, penetrated to low altitude and disintegrated catastrophically. Only small fragments, slowed by the blast and stripped of most of their kinetic energy, ever reached the surface, more like falling debris than supersonic bullets. They'd bury themselves shallowly, if at all, and weather away in a sea of peat and snow. That doesn't mean there's nothing to find. Tiny spherules of exotic glass, chemical anomalies in tree resin and soil, subtle isotopic fingerprints. Those can all testify to a cosmic visitor without the need for a smoking hole, and researchers have in fact found such clues, though interpreting them is its own argument. The missing crater, then, is not just an absence. It's a filter that any theory of Tunguska has to pass through. If your explanation requires a big, obvious impact structure, it dies on the evidence. If it allows, or even demands, that all the carnage came from a mid-air disintegration, it stays alive. Meteorite buried in a bog, crater eroded away, or airburst that never touched the ground as a solid object. These are the three broad stories competing to explain that silent forest. Over the last century, the balance of evidence has steadily shifted toward the last one, but agreeing on airburst is like agreeing that a gun went off. You still have to ask, what pulled the trigger, and what exactly was in the chamber? Was it a rocky asteroid, an icy comet fragment, something in between, something stranger? To answer that, you have to stop staring at the missing hole and start looking for microscopic shrapnel, chemical smoke rings, and the faint fingerprints an explosion leaves behind in the environment. The crater might be missing, but the blast had to leave traces somewhere. Out in space, before it ever met our atmosphere, the thing that caused Tunguska would have looked unremarkable. Not a glowing fireball, not a sci-fi death rock with flames and sparks trailing behind it, just another dark object, cold, airless, minding its own business on an orbit that happened, by bad luck for Siberia, to cross Earth's path on a late June morning. But out there, in that quiet vacuum, what it was made of already sealed the fate of the forest. Space rocks come in flavours. 3 big categories matter for Tunguska: stony asteroids, iron asteroids, and comets. A stony asteroid is, in the simplest sense, a rock. Mostly silicate minerals, like a piece of the mantle or crust of a shattered world. Some are tough, coherent blocks. Others are rubble piles, collections of fragments held together loosely by gravity, and a little bit of dust as glue. Their densities vary, but they're generally in the ballpark of solid rock. An iron asteroid is completely different. It's metal, mostly nickel-iron alloy, forged in the centre of a larger body that melted and differentiated long ago, then got smashed apart in some ancient collision. Iron bodies are dense, strong, and incredibly hard to destroy. When they hit our atmosphere, they're like armour-piercing shells, and then there are comets. Comets are often called dirty snowballs, but that phrase is almost too generous to the snow. They're low-density mixtures of dust, rock, organics, and ices: water ice, carbon dioxide ice, carbon monoxide, ammonia. They are fragile, porous, and riddled with volatile material that wants to vaporize the moment things get warm. Bring each of those 3 ingredients down into the atmosphere at cosmic speed, and they behave like 3 different weapons. A solid iron body tends to hold together. It burns, it ablates, it loses mass, but it can punch deep into the atmosphere and very often survive to strike the ground. That's how you get classic iron meteorites buried in craters, like at Arizona's Barringer crater. A coherent stony body is in between. Some make it to the surface intact or in a few big pieces. Others break apart in flight, with an airburst plus a meteorite shower of surviving fragments. A cometary fragment is the opposite end of the spectrum. Low density, full of ices and internal voids, it is exquisitely vulnerable to the stresses of entry. The same atmosphere that an iron bullet can pierce like tissue paper can behave like a brick wall to a fragile half-empty snowball. And that's where Tunguska lives, at the intersection of what came in and how it died. 3 main knobs control that death: speed, angle, and strength. Speed first. Earth orbits the Sun at about 30 kilometers per second. Asteroids and comets also have their own orbital velocities. The closing speed when one hits our planet can range from about 11 kilometers per second, barely falling in, up to more than 70 kilometers per second for a retrograde comet coming head-on. That speed sets the kinetic energy. Energy scales with the square of velocity. Double the speed and you quadruple the energy, all else equal. It also sets the dynamic pressure, the crushing force of the air on the front surface of the object as it rams into thicker layers of atmosphere. The faster you go, the faster those forces and temperatures ramp up. Angle is the second knob. A steep, almost vertical entry path drags the object through a shorter column of air. It slams into denser layers quickly, but it also has less time to lose speed before reaching low altitude or ground. A shallow, glancing path makes the object plough through a long atmospheric track, losing energy over many hundreds or thousands of kilometers, and tends to disintegrate higher up. Strength is the third and most mysterious. It's not just about what the object is made of, but how it's put together. Solid iron has huge compressive and tensile strength. A fractured, stony body has lower strength. Cracks act as pre-existing weaknesses. A porous, icy cometary fragment can be so fragile that the stresses of entry tear it apart like a sandcastle hit by a wave. Fragmentation happens when the dynamic pressure from the air exceeds the material strength of the body. At some altitude, the outside is being crushed, heated, and ablated while the inside is still cold and brittle. If the internal structure can't transmit and equalize those stresses quickly enough, the object catastrophically fails. A strong, dense object might barrel all the way down to a kilometre or less above the ground before it pops, or never pop at all, simply ploughing into the surface. A weak, low-density object might shatter tens of kilometres up, its energy spread and diluted before it ever gets close to the trees. Tunguska's flattened forest and lack of crater tell us something about where, in that spectrum, the culprit sat. The blast modelling that best matches the pattern of tree fall, the central standing zone, and eyewitness reports points to an explosion somewhere between about 5 and 10 kilometres above the ground. Not as high as Chelyabinsk's 30 kilometres, but not right above the treetops either. Powerful enough that the shock wave still had teeth when it hit, but high enough that the impactor itself never struck the surface as a single solid lump. That middle altitude airburst is the first clue. It doesn't automatically decide the case, but it constrains the options. If you prefer a comet, you imagine something relatively low density, perhaps 0.5 grams per cubic centimetre, half the density of water shot through with ice and voids. Coming in fast, maybe 30, 40, even 50 kilometres per second, on a slightly steeper trajectory. In that picture, the stresses ramp up violently as it dives into thicker air. It breaks at higher altitude than a comparable stony asteroid would, and much of its mass vaporizes into fine dust and gas, spread over a huge volume. A cometary body like that leaves a particular kind of signature. You'd expect low-density behaviour, lots of ablation and fragmentation, minimal large fragments making it to the ground, high-altitude dust, a plume of very fine particles injected into the stratosphere, capable of circling the globe. Some historical accounts in 1908 and 1909 mention unusually bright night skies in Europe, noctilucent clouds, and a strange silvery twilight that some researchers have linked to Tunguska dust in the upper atmosphere. Weak chemical fingerprint. Comets do contain metals and rock, but per unit mass, an icy comet leaves less dense rain of metallic debris than a solid asteroid. Its long-term environmental footprint in soil and tree rings might be faint, drowned out by normal background infall of micrometeorites. Advocates of the comet hypothesis lean hard on those features. They point out the lack of obvious meteoritic fragments at the site, the challenges of finding strong iron or stony debris, and the global reports of optical anomalies in the months after the blast. An icy interloper, they argue, can deliver megatons of energy, flatten a forest, and yet melt into vapour and dust without leaving a heavy metallic corpse behind. If you prefer a meteorite, a rocky asteroid, the story shifts. Asteroids in near-Earth orbits generally hit at lower speeds than long-period comets. Something like 12 to 25 kilometers per second is common. That lower speed reduces the specific energy a bit, but if the object is denser and stronger than a comet, it can still penetrate to low altitude before failing. A 50-80 meter stony asteroid with a density around 2.5 to 3 grams per cubic centimeter, entering at maybe 15 to 20 kilometers per second, would carry enough punch to survive deep into the atmosphere and then blow apart in a single massive event at 5 to 10 kilometers up. That matches a lot of Tunguska blast models. Crucially, a rocky body like that is rich in metals and minerals that don't just vanish, they melt, they vaporize, they condense again as the fireball cools. They fall out of the sky as microscopic and millimetric droplets of glass and metal, spherules, scattered over the downrange footprint. It also carries distinctive elements and isotopes. Nickel, cobalt, iridium, certain platinum group metals. The ratios of these elements in many meteorites differ from those in normal Earth rocks. Trace amounts of such material, distributed in peat and lake sediments, can act like pollen from the impactor, still detectable decades later. That's where the microscopic shrapnel hunt comes in. Over the years, teams have dredged Tunguska's bogs and lakes, cored its peat, scraped the resin from trees that were alive in 1908, and filtered the sediments looking for tiny foreign beads. They found them. Magnetic spherules, sometimes enriched in nickel and other meteoritic markers, show up in layers dated to the time of the blast. Some chemical analyses, especially of unusual particles in lake beds and peat, suggest a composition resembling stony chondritic meteorites. Other work has argued for more exotic, even carbonaceous material. To a meteorite proponent, that's the smoking gun. A rocky body shattered in the air, sprayed its guts across the landscape, and those guts now sit entombed in the soil as chemically anomalous beads and grains. But the picture is not clean. Some studies report that the concentrations and compositions of spherules at Tunguska are not unique, that similar levels turn up elsewhere from the normal background drizzle of cosmic dust. Others argue the particles are consistent with terrestrial sources like industrial pollution or volcanic ash. Dating layers in peat and lake sediments is imprecise. Contamination is easy. On top of that, some measurements have suggested an unusually low mean density for the Tunguska object, based on its fragmentation height and the spread of the shock wave, more in line with a weak porous body than a solid rock. That points back towards a comet, or at least a very fluffy asteroid. So which was it? If you weigh the arguments, you can tilt the scale either way. Tunguska's relatively deep penetration and intense localized blast feel comfortable for a modest-speed stony asteroid with low but not ridiculous strength. The chemical and spherual evidence, if you take the more optimistic interpretations, fit that picture. The lack of large meteorites is annoying but not fatal. If the body exploded high enough and thoroughly enough, big chunks might simply not exist. On the other side, the absence of clear, heavy meteoritic debris, the hints of low density from modelling, and the probable injection of high-altitude dust that lit up European skies sound pleasingly comet-like. A fragile, volatile, rich fragment could absolutely deliver a Tunguska-class airburst and then disappear almost completely, leaving only faint chemical whispers behind. There's a third, messier possibility too, something in between. Many near-Earth objects are transitional, extinct or dormant comets whose ices have mostly cooked away, leaving a weak, carbon-rich rubble pile asteroid behind. From a distance, you can't easily label them asteroid or comet. They're hybrids scarred by eons of sunlight and outgassing. A body like that would behave neither like a classic iron nor like a pristine, fluffy comet nucleus. It would be low density but rocky, volatile poor but structurally weak. In other words, almost custom-built for a Tunguska-style airburst. Right now, the data we have don't let us pin it down with the precision we'd like. Each new chemical analysis, each reinterpretation of the blast dynamics, nudges the needle a bit, but it doesn't slam it to one side. The question, meteorite or comet, remains open, not because we haven't looked, but because Tunguska sits at the fuzzy boundary between those categories. The object was small, the explosion destructive, the environment forgiving to erasure. A century of moss, snow and fire has blurred the crime scene, so investigators have turned increasingly to the tiniest surviving witnesses, the glass beads, the chemical smudges, the isotopic ratios hiding in a gram of mud or a scrap of bark. If you can't find the bullet and you'll never see the crater, you read the smoke in the air, the dust on the windowsill, the trace elements that shouldn't be there. That's where the story goes next, into microscopes and mass spectrometers, trying to read Tunguska's identity from fingerprints so small you could miss them in a sneeze. When scientists finally started going back into Tunguska in force, decades after the blast, they weren't just wandering around hoping to trip over a chunk of alien metal. They brought a different kind of question. If a cosmic object exploded here, what did it shed? Every meteor, every cometary fragment that hits Earth, carries with it a chemical accent, a pattern of elements and isotopes that doesn't quite match the local dirt. Think of it like a foreign pollen cloud blowing through a forest. Even if the flowers that produced it are long gone, some of their grains will get trapped and stored in whatever natural recorders happen to be around. At Tunguska, those recorders are everywhere. The first one is the trees themselves. Conifers around the blast site were alive in 1908. Their branches were coated in whatever rained out of the sky that day, and in the months that followed, ash, soot, dust, vapour that condensed into microscopic droplets of glass and metal. Tree resin is sticky, hydrophobic and chemically conservative. It traps particles, seals them away from rain and decay, and can hold them for more than a century. Slice into a bead of old resin, dissolve away the organic matrix carefully, and you're left with whatever hard specks got stuck there the day the sky exploded. The second archive is peat. The Tunguska region is full of bogs, places where plant material grows, dies, and accumulates as a slow-building carpet. In oxygen-poor water, decomposition crawls. Year after year, a new millimetre or two of organic mush is layered on top of the last. Drop anything that doesn't rot quickly into that, and it's entombed in a chronological stack. Dig a core out of a peat bog, date each layer, and you get a timeline. Somewhere in there should be the summer of 1908. The third record is at the bottom of lakes and ponds. Quiet basins accumulate fine sediments, clay, silt, organic flakes settling slowly through still water. Anything falling out of the sky that's small enough to stay aloft for hours or days has a good chance of winding up in that soft, undisturbed mud. Once buried, it's shielded from surface contamination in a way tree bark and soil are not. So beginning in the 1960s and 70s, and continuing fitfully ever since, researchers took cores, scraped resin, sieved sediments, and marched it all back to laboratories. There, they did the microscopic equivalent of panning for gold. Under the microscope in the layers corresponding roughly to 1908, they began to see them. Tiny, near-perfect spheres and droplets. Some were glassy, translucent. Others were opaque and metallic. Some were magnetic. These are microspherules, or spherules for short, little beads formed when material melts or vaporizes, and then cools rapidly while still airborne, surface tension pulling it into a ball. Spherules by themselves are not unusual. Earth is constantly bombarded by dust and micrometeorites. Volcanoes and fires can make them too. The interesting question isn't, are there spheres, but are there more than usual, and what are they made of? Several studies have claimed that in the layers dated to just after 1908, the concentration of magnetic and glassy spherules in Tunguska, peat and lake sediments jumps. Not by a factor of 2 or 3, but by 10, 50, even 100 compared with layers above and below, or with control samples from elsewhere in Siberia. That kind of spike is exactly what you'd expect from a big atmospheric explosion dumping a cloud of finely divided debris over a limited footprint. Then came the chemistry. If the spherules are just local rock melted by the blast, they should have element ratios similar to Siberian crustal material. Mostly iron, silicon, aluminum, a normal spread of minor and trace elements. If they're mostly meteorite guts, they should show patterns we associate with certain classes of space rock. Elevated nickel, cobalt, iridium, and platinum group elements, particular ratios between them. Sometimes unusual isotopic signatures of elements like oxygen or chromium. Some of the Tunguska spherules tick at least part of that meteoritic box. Analyses have found beads rich in iron and nickel with nickel contents in the 5 to 10% range, higher than typical terrestrial magmas, closer to what you see in chondritic meteorites. Others show platinum group metals bumped up above local background. A few glassy particles carry element ratios that line up better with average cosmic dust than with river sand or volcanic ash. There are claims of non-terrestrial isotopic ratios, hints that the oxygen in some grains doesn't quite match the signature of local rocks. Put all of that on a poster, and you can draw a neat arrow from foreign chemistry to extraterrestrial impactor. This is the narrative. A stony chondritic asteroid shatters in the atmosphere. Its molten spray cools into droplets. Those droplets fall onto trees and bogs and lakes, and a century later we pick them out of the mud. Their composition is the fingerprint of the parent body, telling us it was rocky, metal-bearing, decidedly not just a ball of ice. But the story never stays that clean for long. The first problem is that Earth is dusty. Every year, tens of thousands of tons of micrometeorites and cosmic dust settle out of the atmosphere all over the planet. If you scoop up enough peat or lake mud from anywhere, you will find spherules with meteoritic chemistries, simply because they've been sifting down for millions of years. Tunguska isn't just a crime scene, it's also a collector's plate for that background rain. The second problem is that peat and lake cores are not perfectly labelled jar shelves in a lab. Layers can get mixed by roots, burrowing insects and freeze-thaw cycles. Dating them precisely to, this one is exactly 1908, is hard. Radiocarbon, pollen markers, even the record of atmospheric nuclear tests help, but uncertainties of several years or decades are common. If your Tunguska layer is actually smeared over half a century, you might be averaging a rare event with normal background. Then there's contamination in the human sense. Some samples were collected in the 20th century with methods that would not pass modern clean lab standards. Metal tools, unfiltered air, storage in ordinary containers. Industrial pollution can add its own metallic spherules. Distant factories and power plants spit out fly ash that drifts and falls like any other aerosol. Later studies have pointed out that some anomalous particles are remarkably similar to known industrial byproducts. Because of that, the literature on Tunguska's microscopic fingerprints reads less like a single clear verdict and more like an argument. One group reports an iridium spike in peat dated to 1908 and calls it smoking gun evidence of extraterrestrial matter. Another re-examines peat from the same region, finds no such spike, and suggests the original result was an artifact of sloppy normalization or sample handling. A team finds unusually nickel-rich spherules in a lake core and interprets them as asteroid droplets. A different team points out that similar spherules appear in lakes far from Tunguska too, at levels not obviously lower. Isotope results are even trickier. Measuring tiny differences in isotopic ratios demands ultra-clean procedures and enough sample material to average out noise. Some early non-terrestrial signatures have not held up under reanalysis with newer equipment. Others remain suggestive but not definitive, close enough to Earth values that you can't rule out unusual but still terrestrial sources, all of which leaves us in a familiar place with this mystery. There is smoke, but not everyone agrees how much or which fire it came from. If you take the most careful, skeptical line through the data, you can still say this. Tunguska's natural recorders do seem to show some anomalies around the time of the blast. There are layers with elevated spherule counts. Some of those spherules look and behave chemically like meteoritic material. There are hints of trace element enrichments consistent with an extraterrestrial contribution. None of it is so overwhelming that it would have shouted impact to a blind analyst unaware of the history. But taken together with the flattened forest and the eyewitness reports, it fits comfortably into an airburst from a stony or mixed composition object. It also fits a more fragile comet-like body, if that comet carried embedded rocky and metallic grains, as we know many do. Comets are not pure ice, they're dirty, dusty aggregates. The dust part of a comet can be chemically similar to carbonaceous chondrites, another class of meteorite with distinctive trace elements. Vaporize that dust in an airburst, and its cooled condensates will look meteoritic in much the same way an asteroid's would. Which brings us back to that nagging thought. If something from space did this, where are the big pieces? For many people, the lack of obvious meteorites at Tunguska is still the sticking point. We know what it looks like when a hefty chunk hits the ground. Arizona's Barringer crater is littered with iron meteorites. Sikhote-Alin, another Siberian fall in 1947, showered the taiga with thousands of metallic fragments. Why doesn't Tunguska have its own collection of museum pieces? Because the physics doesn't require them. In a mid-altitude airburst, most of the energy is released while the object is still moving very fast, high enough that the pressure and temperature in the fireball can rival those in the outer layers of the sun. Under those conditions, rock doesn't just crack. It melts, boils, and dissociates into vapor. Small fragments can be fully ablated, eaten away by the incandescent sheath of compressed air surrounding them. Others are broken down into gravel-sized pieces that decelerate rapidly, lose most of their kinetic energy to heat, and fall as anonymous stones indistinguishable from local rock, unless you analyze them grain by grain. Chelyabinsk in 2013 is the modern cautionary tale. That object was a stony asteroid, similar in size to many Tunguska estimates. It exploded about 30 kilometers up with an energy of several hundred kilotons. There is no large crater in Chelyabinsk. There is no multi-ton space rock on a pedestal. Instead, Devers recovered a few fragments from a lake, the largest roughly 0.5 meter across, plus thousands of much smaller pieces scattered over a wide area. Most of the original mass was turned into dust and microscopic droplets that we only know about because people went looking very deliberately. Scale that up in energy, push the explosion down to 5 to 10 kilometers, and drop it into one of the most remote, swampy, snow-covered regions on Earth in 1908, and the odds of casual discovery of surviving chunks plummet. Any decimeter or meter-sized fragments that did reach the surface could have buried themselves in soft ground, sunk into bogs, or weathered into the background. Finding them now would require systematic, fine-grained magnetic surveys and drilling, a level of effort that has barely been attempted at Tunguska, compared with more accessible sites. So, No big fragments does not mean no space object. It means the object failed where the air was thickest and the stress is highest, in exactly the regime where destruction is maximized and survivorship minimized. The evidence we're left with is necessarily subtle. A broken forest, a pattern of shock, faint anomalies in peat and resin, beads of metal and glass smaller than a grain of sand. The fingerprints are there, but they're smudged, overlain by a century of natural and human noise. And while the chemistry hints strongly at something extraterrestrial, it stops just short of telling us, cleanly and finally, what that something was. To push further, researchers have to move beyond the obvious signatures of rock from space and into harder questions. Exactly how much energy was released, how it coupled to the atmosphere and ground, and what that implies about the size, speed, and density of the intruder. That trail leads from microscopes to blast models, from muddy cores to equations about shock waves and fragmentation. To understand what kind of object can flatten 80 million trees and yet leave almost nothing we can hold in our hands, we have to get serious about the energy budget. If Tunguska is a crime scene, the broken trees are the blood spatter. They don't just say something happened, they encode how hard, how fast, how close. This is where the energy question starts. When a shockwave from an explosion moves through a forest, it doesn't behave randomly. There's a threshold pressure at which tree trunks snap, another at which they're uprooted completely, another at which branches strip but trunks remain standing. The angle of fall points back toward the source like arrows on a map. The distance from the epicenter to where trees are only scorched, not felled, tells you where the blast stopped being deadly and started being just impressive. So researchers take what was left of that pattern. Photographs from the 1920s and 30s, survivor trees still bearing scars decades later, aerial surveys from the Soviet era, and treat it like forensics. They sketch out rings, zones where trees were blown down and lined, zones where they were snapped but not uprooted, zones that show only scorching or broken branches. Then they ask a brutal question. What kind of overpressure does it take to do this? In blast physics, overpressure is the amount by which the transient shock wave exceeds normal air pressure. A few kilopascals? Windows break. Tens of kilopascals. Walls fail. Weak structures collapse. Push it higher, and you're in the regime where living trees, flexible, rooted, evolve to ride out storms or go down like matchsticks. By comparing Tunguska's treeful pattern to pressure damage curves from nuclear tests and chemical explosions, you can back out an approximate shock strength on the ground at various distances from the hypocenter, the point directly beneath the blast. Once you know that, you can work backwards through atmospheric blast models to estimate how much energy had to be dumped into the air in the first place. That's the basic idea. On paper, not terribly complicated. Observed damage leads to inferred overpressure, leads to modeled explosion energy. In practice, it's a mess of assumptions. First, you have to decide exactly how strong a shock is needed to blow down Siberian larch and spruce at different sizes and ages. Those numbers aren't written into nature, they come with uncertainties. Then there's the forest itself. The 80 million trees figure isn't a precise count. The density of the stand, the mix of species, the condition of the soil, seasonal moisture, all of that controls how easily trunks snap or uproot. You also need to know the height at which most of the energy was released. An explosion 5 kilometers up couples very differently to the ground than one at 10 or 20. Change any one of those knobs and the energy estimate shifts. That's why published numbers for Tunguska's yield are all over the place. Some early Soviet analyses, based on damage within a radius of about 20 kilometers, suggested an energy release equivalent to roughly 10 to 15 megatons of TNT. Later work, incorporating a larger area of significant treefall and different assumptions about tree strength, pushed that into the 20 to 30 megaton range. There are models that go higher still, hinting at 40 or even 50 megatons, though those sit at the edge of what most researchers now consider plausible. On the low side, a handful of analyses have tried to reconcile Tunguska with energies closer to 3 to 5 megatons, arguing that the forest may have been particularly vulnerable and that some reported blast radii were exaggerated or misinterpreted. But those low-yield models struggle to reproduce the wide swathe of heavy damage and the intensity of shock reported by witnesses up to 60 kilometers away. Most modern estimates cluster in a rough band, somewhere around 5 to 30 megatons. It's a wide window, but even the low end is enormous by human standards. To get a grip on those numbers, you have to put them next to things we actually know. The Chelyabinsk airburst in 2013 is the most obvious comparison. That object, about 18 to 20 meters across, released an energy equivalent to maybe 400 to 600 kilotons of TNT when it exploded around 30 kilometers up. It broke windows across a huge city and injured over 1,000 people, mostly from flying glass, but it did not flatten forests. The shock was still too weak by the time it reached the ground. Scale that up by a factor of 10 in energy, and you're in the low megaton range. Double it again, and now you're in the early Tunguska estimates. Take a few more steps, and you're knocking on the door of the largest nuclear test ever conducted. The Soviet Tsar bomber in 1961, at about 50 megatons. Some Tunguska reconstructions, especially the higher yield ones, put the blast in that same league. But this is where altitude matters, a lot. Tsar bomber was detonated at about 4 kilometers above sea level over Novaya Zemlya, and the test films show something that looks disturbingly similar to Tunguska eyewitness accounts. A flash, a rising column, a mushroom cloud, a pressure wave moving out over the landscape. Yet the way that wave couples into the ground depends sensitively on the height of burst. Too high, and most of the energy just inflates the atmosphere. The ground feels only a soft slap. Too low, and more energy goes into cratering an ejector than into a wide blast wave. For Tunguska, reconstructions based on witness angles of light and sound, along with the pattern of fall, generally place the main energy release somewhere between 5 and 10 kilometers above the ground. That's low enough for strong coupling, but high enough that no big crater forms. It's the sweet spot for an airburst designed, by indifferent physics, to maximize damage over area without punching a hole. Push the detonation point up to 15 or 20 kilometers like Chelyabinsk, and many of those 80 million trees probably survive. Drop it to 1 or 2 kilometers and you might get a shallow crater and concentrated devastation, but the blast radius shrinks. So when you see a Tunguska energy estimate, there's an invisible chain hanging behind it. Assumed altitude, assumed speed of the object, assumed entry angle, assumed tree strength, assumed atmospheric conditions. Each team of researchers tweaks those inputs differently, and the megaton number slides accordingly. Different modelling approaches make it worse. Some use semi-empirical scaling laws derived from nuclear weapons testing. Basically, if you gave a bomb of this yield this altitude, you'd expect this damage radius. Others run detailed hydrodynamic simulations of a stony object breaking apart, compressing air and depositing energy as it comes down. Some treat the impactor as a rigid sphere until it fails catastrophically. Others model it as a fragile rubble pile that starts shedding mass far higher in the atmosphere. If you assume a tougher, denser object that stays intact until it's deeper in the atmosphere, you tend to get a more concentrated, lower altitude blast that can flatten trees with a bit less total energy. If you assume a fluffy, comet-like object that disintegrates early and spreads its energy over a taller column of air, you may need a larger initial energy to produce the same ground effects, and that's where the energy debate folds back into the original mystery. What was this thing made of? Energy is not a property of the object alone, it's a property of its mass and its speed. Kinetic energy scales with the square of velocity. Double the speed and, all else equal, you quadruple the energy. Typical near-Earth objects hit the atmosphere at anywhere from 11 kilometers per second. The minimum for something gravitationally bound to Earth's orbit, to over 70 kilometers per second for retrograde comets. Most sit in the middle, 15 to 30 kilometers per second. If you pick a representative speed, say 20 kilometers per second, and an energy of 10 to 15 megatons for Tunguska, you can back out a mass. Choose a plausible density for the impactor material, higher for solid rock or iron, lower for an icy porous comet nucleus, and that mass tells you a diameter. Models that favour the lower end of the energy range, 5 to 10 megatons, along with typical entry speeds and stony asteroid densities, tend to give you an object maybe 40 to 60 metres across. Crank the energy up into the 20 to 30 megaton band, and you're looking at something closer to 60 to 100 metres in diameter if it's rock, smaller if it's metal, larger if it's mostly ice and voids. A denser, stronger object can be smaller and still deliver the same punch. It ploughs deeper before it fails. A weaker, fluffier object has to be bigger for the same energy budget, and it usually explodes higher up, spreading its energy in a way that's less efficient at tree-level flattening. So when one paper argues that Tunguska was a stony asteroid 50 meters in diameter, and another proposes a porous, comet-like body 100 to 200 meters across, They're not necessarily contradicting each other about the forest. They're disagreeing about how quickly the intruder shredded itself and how its energy was distributed on the way down. The comparisons to human explosions sharpen the stakes but also highlight the limits. We have detailed data from nuclear tests across a range of yields and altitudes, so it's tempting to say Tunguska was like a 15 megaton bomb at 7 kilometers altitude. But an asteroid is not a bomb. Nuclear devices deposit their energy almost instantaneously in a compact volume. An incoming space rock spreads its energy along a path tens of kilometers long, bleeding mass, fragmenting, flaring and pulsing as it goes. The end result, a fireball and a blast wave, is similar enough for rough analogies, but not identical. Still, those analogies are hard to avoid. Even at the conservative end of 5 to 10 megatons, Tunguska released on the order of hundreds of times the energy of the Hiroshima bomb. At the high end of commonly cited estimates, it rivals or exceeds Tsar Bomba. And all of that came from a single chunk of cosmic debris smaller than a city block. That's the unsettling takeaway of the energy question. You don't need a dinosaur killer for local catastrophe. A modestly sized asteroid or comet fragment, moving at cosmic speed, can deliver the energy of the largest human-made explosion in history and erase a forest the size of a small country in less time than it takes to draw a breath. And yet, despite that colossal power, the way that energy is released, high in the sky, spread along a path, turned into shock and heat rather than a crater, means it can leave behind almost nothing solid we can hold, no obvious smoking gun bigger than a few grams. The numbers, the models, the arguments over megatons and meters are not just academic. They tell us what kind of threat Tunguska represents in the modern world, how often we might expect something similar, and whether we're looking mostly for hard, rocky bullets or fragile, dusty snowballs out there. To see what that really means for Earth's biosphere and for us, you have to zoom out from blast equations and look at what actually happened to the land that took the hit. A forest knocked flat in seconds, and then, somehow, it grew back. If you had walked into the Tunguska forest in the summer of 1907, it would have looked like any other slice of Siberian taiga. Endless ranks of larch and spruce, peat bogs, clouds of mosquitoes thick enough to seem like weather. Walk in on June 30th, 1908, and it would have looked like the end of the world. The blast didn't just topple trees. It did three main things to the ecosystem in the first few seconds. First, the shockwave itself. Over an area of more than 2,000 square kilometers, trunks snapped and uprooted, crowns sheared off, branches stripped. Near the epicenter, trees were not just knocked down. They were pulverized into splinters and stumps. The canopy, that layered structure of leaves and needles that moderates light and temperature below, was turned into an open plain in moments. Second, thermal radiation. Witnesses described a fire that covered the sky, a flash so intense that people felt heat through their clothing, and dry brush ignited at distance. That radiant energy and the hot air in the wake of the fireball scorched bark, desiccated needles and lit ground fires. In the central zone, trunks were stripped of branches but left standing, baked and dead. A telegraph pole forest of ghostly stems, killed by heat and shock but not toppled because they were directly under the blast. Third, the air itself moved. The downward rush of superheated, turbulent air following the explosion drove flames across the forest floor. Patches of peat, Siberia's slow-accumulating carbon bank, caught fire. Aerial photos, decades later, show sinuous burn marks, dark scars where surface fires ate into the soil. Every animal in that zone had to deal with that sequence: flash, shock, wind, fire. There are scattered reports of charred reindeer carcasses, of birds falling from the sky, of game disappearing for years from areas closest to the blast. Smaller creatures, rodents, insects, the endless armies of beetles that live in dead wood, would have been hit unevenly. Many would die instantly. Others, just outside the lethal core, would find themselves in a suddenly altered world, their burrows intact, the forest above them gone. From a human perspective, it was devastation. From an ecological perspective, it was a very large disturbance. And ecosystems, especially boreal forests, know what to do with disturbance. The taiga is already tuned to catastrophe. It burns regularly. Lightning strikes, droughts, human-set fires. All of these periodically reset patches of forest. The species that dominate there are not delicate cathedral trees that need centuries of quiet. They're opportunists designed to ride fire cycles. So after Tunguska, the forest did what it always does. Within weeks, char and ash and splintered trunks became a new substrate. Heat opened the cones of fire-adapted species. Seeds that had been waiting in the soil for years suddenly had light and space. Grasses and forbs colonized the newly sunny ground, stabilizing the soil and bringing in herbivores. In the first few years, the blast zone would have looked more like a meadow than a forest. Shrubs, pioneer trees, wildflowers, flushes of mushrooms feeding on the sudden bonanza of dead wood. Dead trunks lying in ordered rows did not just record the direction of the blast. They became nurse logs, slowly rotting platforms that hold moisture, shelter insects, and give seedlings a boost above the raw, often waterlogged soil. Fungi invaded them, breaking down lignin and cellulose, moving nutrients back into circulation. As the second decade rolled around, young trees began to dominate. Spruce and larch grew through the shrub layer. In many areas, the regrowth was surprisingly dense. With the original canopy gone and nutrients unlocked by fire, saplings could pack in at high density, racing each other for light. From above, what had been a flattened fan of grey and black slowly turned into a lighter green fuzz, then a darker, continuous swath. By the time Kulik trudged into the epicenter in the late 1920s, two things were visible at once: the catastrophe and the recovery. The radial pattern of fallen trunks still lay across the landscape, a frozen shock wave etched in wood. But around and between those old corpses, a young forest was already well underway. Some places looked like clear-cuts after logging, old stumps, young stands. Others were rough mosaics of untouched patches, blowdown, and different successional stages, depending on exactly how the shock and fire had played out at the microscale. Give the system a few more decades and even that contrast starts to blur. Shade-intolerant pioneers give way to slower, more shade-tolerant species. Litter accumulates again, moss and peat rebuild, light levels under the canopy drop, and the forest begins to resemble what was there before, at least to a casual glance. But if you know what to look for, the forest remembers. One of the most powerful memory systems in a landscape like this lives inside individual trees, their rings. Each year, a tree in a temperate or boreal climate lays down a new ring of wood. Wide rings usually mean a good growing year, enough warmth, water, and light. Narrow rings can flag droughts, pest outbreaks, unusual cold or physical damage. Abrupt shifts, rings that suddenly get much narrower or wider, often mark some ecological shock. Tunguska sits right in the period where we have good, continuous tree ring records from Siberia. Dendrochronologists have sampled living trees near the epicenter and compared them with control trees farther away. Many of those local sequences show something striking. A sudden drop in growth starting in 1908, lasting for a few years, followed by a period of unusually rapid growth. That pattern makes sense. Surviving trees near the blast would have had their crowns scorched or shredded. With fewer needles, they photosynthesized less, laid down skinny rings. But then, with competitors gone and more light available, those same trees could rebound, widening their rings in subsequent years. Young trees that sprouted in the blast zone also often show rapid early growth. You're a seedling in prime real estate, with full sun and a nutrient windfall. Tree ring studies also let researchers test wilder claims. Over the years, people have suggested that Tunguska might have involved exotic physics, a micro-black hole passing through Earth, an antimatter clump annihilating in the atmosphere, even some kind of alien technology mishap. Many of those proposals lean on the idea that the event had radiation-like effects, mutations, growth anomalies, biological damage beyond what simple blast and fire could explain. So what do the trees say? You can look for features in rings that signal ionizing radiation damage, unusual patterns of cell division, spikes of abnormal growth, scars that line up across many individuals in the same year. At the human scale, extensive radiation exposure tends to leave clear signatures in health records and in the genetics of local populations. In Tunguska's case, there were anecdotal reports, people getting sick, livestock dying, strange growth in plants. But anecdote and aftermath are messy. Smoke inhalation, trauma, starvation when hunting grounds vanish overnight. Those alone can make people and animals ill. More systematic attempts to find a radiation fingerprint have not turned up anything like what you'd expect from a nuclear-scale dose of ionizing radiation at ground level. The tree ring shows stress, yes, but patterns consistent with heat injury and mechanical damage. Forest structure shows a blast and fire mosaic, not the kind of uniform, invisible poisoning that radiation would produce. Later, when above-ground nuclear tests genuinely bathed parts of the world in extra radiation, their signature popped out clearly in environmental records: radioisotopes in soil and ice cores, genetic effects in exposed populations. Nothing like that dating to 1908 shows up in the Tunguska region. That doesn't absolutely rule out any exotic mechanism that might produce mostly mechanical and thermal effects, but it does make mysterious radiation a solution in search of a problem. The blast looks, ecologically, like a gigantic version of processes the tiger already knows: high heat, intense wind, abrupt clearing. And that brings us to the most sobering part of the story: how good ecosystems are at erasing scars. From the air today, you can still just barely see the ghost of the Tunguska pattern in some old photos and remote sensing data. The central marsh, the slightly different age structure of trees along certain axes, the odd geometry of wetlands tied to the blowdown. On the ground, if you know the historical reports and poke around, you can still find the occasional veteran, a tree with an old scar, growth twisted in a direction that speaks of some long-ago shove. But the overwhelming impression is of a normal, functioning Siberian forest. Birds nest, wolves hunt, reindeer migrate through. The trophic webs have rewoven themselves, nutrient cycles have reclosed. Unless you're an ecologist, a geophysicist, or someone obsessed with impact events, you wouldn't know you were standing in the footprint of a many megaton blast. In a sense, that's comforting. It means that even enormous disturbances, ones that momentarily dwarf anything humans have ever built, can be absorbed by Earth's living systems. Fire-adapted forests regrow, soils rebuild, animal communities recolonize. Life is, if nothing else, stubborn. But this resilience has a darker implication for our detective work. Every year that passes, microevidence from Tunguska decays or is overprinted. Tiny spherules weather. Chemical anomalies are diluted. Fallen logs rot and collapse. Peat layers mix. The clear blast signature in forest structure becomes fuzzier as succession progresses. Storms blow down new patches, and subsequent fires rewrite the board. Impact scientists often point out that Earth's surface record of smaller cosmic hits is surprisingly thin. Partly that's because oceans swallow craters. Partly it's because plate tectonics and erosion grind the crust. But events like Tunguska add another factor. When the energy is dumped into the atmosphere rather than directly into the ground, the biosphere itself becomes the eraser. A crater, a kilometre wide, will be visible for millions of years in the right environment. A flattened forest can be invisible, to anything but the most careful analysis, within a human lifetime. Tunguska sits in the narrow window where the scar was big enough, recent enough, and in a remote enough place that people went looking and found it before it vanished into the background noise of ecological change. It is both a case study in planetary resilience and a warning about how easily the planet can hide its near misses. If you want to argue that Tunguska was something other than an ordinary, if enormous, cosmic intruder, you have to work against that erasure, against a century of regrowth and decay. The forest has told us what it remembers of the sky that exploded. What's left is to ask whether anything in that memory really demands a stranger explanation. So, if the forest doesn't insist on anything exotic, why do people keep asking if Tunguska was something else? Part of it is the detective itch. Any big unexplained bang in history attracts alternative theories the way a campfire attracts mosquitoes. But Tunguska has a few very specific quirks that make people restless with the standard small asteroid or comet fragments in the atmosphere story. The first is the missing crater. Humans like bullet hole mysteries. If something that big hit us, we expect a scar we can point to on a map. At Tunguska, you walk into the core and it's marsh. Squishy ground, tangled regrowth, no obvious bowl in the rock. Impact scientists will tell you that this is exactly what you expect from a stony object that explodes in the air 5 to 10 kilometers up. Most of the energy couples into the atmosphere, not the crust. The shockwave flattens things, the heat ignites things, but the ground mostly just takes a slap, not a punch. No crater required. Still, the absence feels wrong at a gut level. Kulik himself went hunting for a crater. Generations after him have done the same, probing lakes, mapping microtopography, arguing over whether this or that depression might be the elusive hole. So far, nothing has passed the sniff test. The second itch is the lack of big, obvious fragments. When a meteorite falls in a desert today, people fan out and pick up hand-sized rocks. At Tunguska, we don't have a glass case somewhere with a famous main mass you can go visit. There are tiny spherules, microscopic bits of material in peat and soil that look and feel extraterrestrial. There are some weird pebbles that might be fragments, but nothing like the Hoba meteorite in Namibia or the Sikhotialine iron masses that cratered another part of Siberia in 1947. Add to that a third ingredient: strange stories. Witnesses talked about beams of light, about the sky splitting, about colours and sounds that don't line up neatly with every simulation. Later, villagers told of lingering sickness, of livestock dying, of fire in the sky, that behaved like nothing they'd seen. Some of these accounts were taken down decades after the fact, filtered through memory, gossip, and the desire to make sense of a legend everyone suddenly cared about. Put those together, no crater, few fragments, odd anecdotes, and you get fertile ground for alternatives. Some of those alternatives are relatively down to earth, others are not. Start with the geologic gas bomb. Siberia sits on huge reserves of natural gas and other volatiles trapped in sediments and permafrost. Over millions of years, organic material has been buried, cooked, and stored. In some places, you can literally see gas bubbling out of lakes, smell hydrocarbons in the soil. So one line of thought goes like this: maybe a massive pocket of methane or some other gas accumulated underground. Maybe heat, or a small earthquake, or a lightning strike triggered a runaway release. The gas vents mixes with air, ignites, and you get a gigantic fuel-air explosion, essentially a natural thermobaric bomb under the Tiger. On paper, a gas explosion can absolutely make a big bang. Industrial accidents have levelled neighbourhoods with much smaller amounts of fuel. A cloud of methane the size of a small city going off at once would be spectacular. But to compete with the Tunguska model, a geologic explosion has to carry a lot of weight. It has to explain the radial treefall pattern that points to a single high-altitude blast, with trees under the epicenter left standing. If the source is in or near the ground, the blast tends to propagate differently, with more obvious excavation and a different damage footprint. It has to account for the eyewitnesses farther away who saw a glowing object streak across the sky before the shock arrived. Reports that sound very much like a bolide coming in on a shallow trajectory, not a column of gas rising silently and then igniting. It also has to explain the tiny glassy spherules in the peat that carry an extraterrestrial chemical signature. You can't get those from methane and rock alone. You need something like a chunk of space rock vaporizing. And then there's the global piece. Tunguska wasn't just a local event. The shockwave registered on barographs thousands of kilometers away. Atmospheric waves rippled around the planet. Nights in Europe were unnaturally bright for days, as if the sky had been seeded with fine particles reflecting sunlight. A gas explosion might plausibly generate a big local shock and some smoke. But lifting enough material that high, spreading it enough to make Londoners read newspapers at midnight, that starts to stretch what a pocket of methane can do. Because of all this, the gas bomb hypothesis mostly lives on the fringes. It's not impossible in a laws of physics sense. But stacked against the evidence, it looks like a solution hunting for a problem that's already better explained by something falling from space. Another family of ideas leans into electricity, lightning clusters, upper atmosphere discharges, exotic auroras. We know lightning can be ferocious. Individual bolts can heat air to temperatures hotter than the surface of the sun, generate shock waves that crack concrete, start wildfires that burn thousands of hectares. Some storms unleash barrage after barrage of strikes, creating complex electrical and acoustic phenomena. There are also stranger lights in the sky. Sprites, jets, elves, whimsically named forms of high-altitude lightning that shoot upward into the ionosphere instead of downward to the ground. These weren't even documented until late in the 20th century, and they remind us that the atmosphere can still surprise us. So what if Tunguska was some kind of runaway electrical event? A colossal megastorm discharging in one titanic flash? A cluster of strikes concentrating energy into a focused blast? Maybe even a rare coupling between solar activity and Earth's atmosphere that dumped energy into the air above Siberia? It's an intriguing thought, but once again we have to ask what such a mechanism would need to explain. It would need to produce tens of megatons of energy in a single burst. That's nuclear weapon territory. Ordinary lightning bolts are many orders of magnitude weaker. Even if you chained millions of them together, you hit scaling problems. The way storms organize, the way charge separates, the way the atmosphere conducts. There's simply no observational or theoretical support for electrical events of that sheer magnitude in the lower atmosphere. It would also have to mimic, almost perfectly, the signature of a fast-moving object depositing energy along a trajectory. The timing of eyewitness reports, the sound delays, the angle inferred from fallen trees, all of those line up with an incoming body, not a stationary discharge blooming in place. And again we come back to the little beads of glass, the chemistry in the soils, the hint of something not from here that got briefly, violently mixed into the upper air. Lightning can melt sand into fulgurites, twisty glass tubes rooted in the ground, but it does not sprinkle a landscape with microscopic spherules whose isotope ratios whisper outer solar system. A third category of ideas is vaguer, unusual atmospheric events. Here the imagination really gets to stretch. Maybe Tunguska was a rogue ball lightning event, scaled up beyond anything we've ever seen. Maybe it was a freak pressure wave generated by bizarre stratospheric dynamics, something like an atmospheric resonance gone critical. Maybe some unknown coupling between layers of the atmosphere focused energy into a small region, like a burning glass focusing sunlight. The trouble with these is not that they're fun to think about. The trouble is that they're almost featureless. They don't come with specific testable predictions. If you say an unknown atmospheric process did it, you can fit any pattern of evidence because your cause has no real constraints. Science thrives on constraints. A comet or asteroid of a certain size and speed makes clear, quantitative predictions. How much energy gets dumped into the air, at what altitude, over what area. You can plug those into models, check them against treefall patterns, barograph records, seismic data, eyewitness testimony. You can be wrong in ways that sharpen the model. Something mysterious in the sky doesn't help you do that. It stays blurry no matter how much data you throw at it. There's a reason you see a kind of hierarchy in how scientists treat these ideas. At the base, you have the simple model, a natural object, of a kind we know exists, following trajectories we can compute, doing things we've observed on other planets and in smaller form in our own atmosphere. That model is not trivial, the details are messy, but it stays within the boundaries of known physics and known populations of space debris. Above that you have more baroque but still physical hypotheses, giant gas explosions, unprecedented lightning clusters, weird atmospheric resonances. These require new mechanisms or huge extrapolations of known ones. They're not a priori impossible, but they need to earn their place by explaining the data better than the simpler model. And hovering beyond those are the truly extraordinary proposals: exotic physics, alien technology, microscopic black holes, clumps of antimatter wandering the galaxy, and occasionally deciding to annihilate in our air. We touched on some of these when we looked for radiation fingerprints and found very little. Here, the bar gets even higher. If you're going to invoke entirely new entities or extremely rare physics, you need exceptionally clear signatures that cannot be matched by mundane mechanisms. Not just an absence of a crater and some weird stories, but hard anomalies in the data that stubbornly resist every conventional explanation. Tunguska doesn't seem to have those anomalies. It has puzzles, yes, uncertainties about the exact composition of the impactor, the precise altitude of the main explosion, the fine structure of the shock. But every dataset we have, forest patterns, global pressure waves, luminous nights, microfragments, leans comfortably toward big, fast object from space exploded in the atmosphere. So why not just slam the door on alternatives and move on? Because curiosity isn't a bug in science, it's the operating system. Minority views, when they're honest and quantitative, serve a purpose. They force the majority model to sharpen itself. What if it was gas? Pushes impact researchers to check geologic maps. What if it was lightning? Nudges atmospheric physicists to show, with numbers, how much energy the sky can actually store and release. Even fringe ideas can have this sharpening effect, as long as they eventually collide with evidence. The trick is learning to walk a narrow ridge. On one side, premature certainty, the temptation to declare the case absolutely closed because the main story hangs together well. On the other, the swamp of anything goes, where every speculation gets equal weight and the absence of evidence becomes evidence of hidden forces. With Tunguska, that ridge is actually in decent shape. The mainstream impact model does most of the heavy lifting. Alternative natural mechanisms are, at best, unlikely side characters that don't solve any problem the main actor can't handle. Exotic scenarios remain entertaining thought experiments. But the mystery isn't entirely dead. There are still details to probe, signatures to refine, possibilities to rule out or, who knows, unexpectedly rule in. And in the last few decades, our ability to revisit old events with new tools has grown dramatically. The same technologies we use to track modern near-Earth objects and model hypothetical impacts can be turned backward, aimed at a dawn over Siberia more than a century ago. So the question shifts from, could it have been something else, to what exactly was the something that fell and how precisely can we reconstruct it? To answer that, we have to bring in satellites that never saw the blast, computers that never felt the shock, and algorithms that can rebuild a vanished fireball from the faint fingerprints it left behind. The strange thing about Tunguska is that almost all of our direct evidence is stuck in time. The trees fell in 1908. The witnesses told their stories in the decades that followed. The barographs, the seismographs, the strange bright nights over Europe, all of that happened once and never again. We don't get a second blast to measure, but we do get a second chance to look. For most of the 20th century, Tunguska research was a boots-on-the-ground affair. People hiked into the marsh, paced off distances, eyeballed directions with compasses and tape measures. They drilled a few cores, sifted a few samples, and tried to stitch a global story out of local scraps. Today, the forest where that shockwave tore through is no longer just a patch of taiga on a map. It's also a high-resolution digital object sitting on hard drives around the world. Modern satellites can see tree lines, swamp boundaries, subtle rises and dips in the ground. Radar can peer through clouds and in some cases even through dense vegetation. Laser scanning, LiDAR, can strip away the canopy and leave you with a ghostly precise image of the terrain underneath. If you feed those data into computers that understand physics, you can do something Kulik and his colleagues could only dream of. You can run the blast backwards. Start with the fallen tree map he drew, refine it with modern aerial and satellite imagery, and you can treat each trunk as a crude vector. This one points northeast, that one southwest. Here the trees are snapped, there they're uprooted. Combine thousands of these little arrows and suddenly a pattern emerges that's sharper than anything a single surveyor on the ground could see. Then you feed that into blastwave models. These aren't guess-and-check sketches on graph paper. They're full numerical simulations that take into account how shock waves propagate through air, how they reflect off the ground, how they fade with distance. The same kind of codes governments use to model nuclear tests and asteroid impact scenarios can be run on the Tunguska geometry. You tell the computer, drop an energy release of X megatons at Y altitude along a path with this angle and speed. Now show me what happens. If your input is wrong, the output doesn't just look a little off, it fails in specific ways. The modelled treeful boundary comes out too small, or too circular, or skewed in the wrong direction. The predicted overpressure at various distances doesn't match barograph records from faraway weather stations. By iterating, changing the altitude, tweaking the impactor's speed and mass, varying the angle, you can converge on a best fit. Not a perfect reconstruction, but a narrow range of possibilities. This is what modern work has been doing, using satellite-informed maps plus high-fidelity blast codes to ask, what combination of parameters best explains what we see? The answers are converging on a particular kind of intruder, a stony body tens of meters across, coming in at a shallow angle, breaking up and dumping most of its energy 5 to 10 kilometers above the ground. Not a skyscraper-sized iron bullet, not a grazing object that skips off the atmosphere, but something in between. That's one big way new tools revisit the mystery. By tightening the box we can put around the invisible object that caused it. But satellites and simulations aren't the whole story. On the ground, later expeditions returned with better eyes and better jars. By the late 20th century, field teams in Tunguska weren't just looking for obvious craters or big chunks of rock. They were sampling systematically. Peat cores from bogs, sediment cores from lakes, soil from undisturbed patches and from the flattened zone. Then, instead of relying on hand lenses and simple chemical tests, they shipped those cores to labs with electron microscopes and mass spectrometers. Under those microscopes, the soil from 1908 isn't just dirt. It's a layer cake of time. You can count down the years in peat, slice across the relevant band, and ask what changed suddenly in that summer. In that slice, you find the tiny glassy spheres, the microspherules that earlier teams had hinted at. But now you're not just noting their existence, you're measuring their composition down to the parts per million. Some of them turn out to have elevated nickel and iridium, trace elements that are common in some meteorites and rare in Earth's crust. Isotopic ratios in certain elements look subtly off, leaning away from the terrestrial norm towards something more solar system-wide. None of this screams smoking gun by itself, but together these lab results sharpen the odds. They tell you that, at the time of the blast, something with a non-Earth-like chemical fingerprint rained down in microscopic form across the landscape. The improved cores also help with another question. What did the blast do to the ecosystem? You can see charcoal spikes, evidence of intense sudden burning. You can detect shifts in pollen deposition, revealing which plants survived, which didn't, and how quickly the forest began to reclaim the scar. In the sediment of lakes downwind, you can look for an influx of fine particles that might have been lofted into the atmosphere and then rained out. Piece by piece, lab techniques take what was once anecdote, the forest burned and grew back, and pin it down with dates and chemistry. All of this modern work circles back to the biggest missing piece in the puzzle, that absent, or at least very shy, crater. If there's one place where new tools have poured gasoline on an old debate, it's a small dark spot on the map, Lake Checo. Lake Checo sits a few kilometers northwest of the blast epicenter. It's long and narrow, like a spoon print, deeper in the middle, with a shape that some people say whispers impact. To its fans, this is the lost crater, hiding in plain sight as a lake nobody paid much attention to for decades. With modern bathymetry, sonar mapping of the lake floor, you can draw a detailed cross-section. Data show a conical depression, with a central mound on the bottom that some researchers argue could be buried impact material. Cores from the lake bed appear to show a disturbance layer not so far below the mud, which some date roughly to the early 20th century. Add to that the fact that some older maps of the region don't clearly show Lake Checo at all, or show something smaller and swampier, and the case starts to look tempting. Maybe this really did form when a fragment of the Tunguska body held together long enough to punch into the ground and make a modest crater that later filled with water. But the Lake Checo story has critics, and they have tools too. Other teams have re-examined the sediment cores and argued that the age estimates are off, that the bottom layers are significantly older than 1908. Seismic surveys of the lake don't show the kind of shattered, chaotic bedrock you'd expect under an impact crater. The shape, they say, isn't so extraordinary for a lake in a region of ice-rich permafrost and sluggish rivers. Then there are the geometry problems. The main flattened tree pattern and eyewitness reports both point to an incoming trajectory that doesn't line up nicely with a fragment hitting where Lake Checo sits today. To make the impact scenario work, you have to posit a complex breakup behavior. One big fragment peels off, follows a slightly different path, and just happens to hit in a way that makes a little cone-shaped hole, but doesn't leave obvious ejecta or a clear halo of impact damage around the shore. Possible? Yes. Necessary to explain Tunguska? Not really. Satellite imagery and precise GPS mapping in the area have only deepened the divide. To some eyes, they show subtle features consistent with an impact scar. To others, they show a perfectly ordinary Siberian lake in a very messy, dynamic landscape. The debate over Lake Checo is a microcosm of Tunguska itself, a tug-of-war between the desire for a clean, photogenic crater and the messy reality that giant atmospheric explosions don't always leave neat holes. While geologists argue over conical depressions, another community has quietly changed how the whole event is framed. Risk scientists. When Tunguska happened, nobody had a catalogue of near-Earth objects, no orbit databases, no all-sky surveys. The idea that space rocks hit planets was still something people argued about. Today, we have decades of telescope work mapping thousands of asteroids, tracking their orbits, estimating their sizes. With those data, we can ask, how often does a Tunguska-class impactor hit Earth's atmosphere? The numbers point to something in the range of once every few hundred to a few thousand years. Not common, but not vanishingly rare either. Combine that with global population maps and you get an unsettling twist. In 1908, that object happened to explode over one of the least populated places on Earth. Slide the blast track a few hours forward or back along Earth's rotation, and that same object could have detonated over a city, or over a coastline crowded with fishing boats, or above a region where witnesses would have been counted in millions, not thousands. From a purely physical standpoint, Tunguska was a natural process. A small piece of the solar system intersected our orbit and dumped kinetic energy into our atmosphere. From a risk perspective, it was something else, a near-miss demonstration. Modern impact risk models treat Tunguska as a calibration point. You take the best estimates of its energy, 10 to 20 megatons, maybe more. You map the damage radius, the level of destruction in the forest, and you ask, what would this look like over New York, over Mumbai, over Lagos? The answers feed into civil defense planning, into international agreements on asteroid detection, into the budgets of sky survey projects. Tunguska is no longer just a Siberian oddity. It's a warning shot that civilization only vaguely heard at the time. And yet, even with satellites, simulations, and risk models, there are things we still wish we had from 1908 and probably never will. We'd love a clear photo of the sky taken in the minutes before the blast, showing the fireball's brightness and trajectory. We'd love seismic records from stations closer to the epicenter, not just the ripples picked up thousands of kilometers away. We'd love pristine, well-dated cores from immediately after the event, cored before modern pollution, before forest regrowth, before war and logging and climate change layered their own signatures on top. Most of all, we'd love an indisputable fragment, a chunk of rock or ice with composition and isotopes that match the microspheres and settle the asteroid versus comet argument for good. The problem is that time is a relentless editor. The taiga is wet, acidic, and biologically active. Small fragments corrode, dissolve, get chewed into the soil cycle. Trees fall, rot, and grow again. Rivers meander, peat layers sag and deform. Every year that passes makes the original signal a little fainter compared to the noise. That's why so much modern work leans on indirect evidence and modelling. We can't rewind Earth. We can only take the traces that remain. Tree directions frozen in old photographs, pressure wiggles in century-old barograph paper, thin dark bands in peat cores, and use modern tools to amplify their whisper. In the end, that may be as close as we ever get. A high-resolution reconstruction with margins of error, anchored by data but never quite closing the door on uncertainty. And that brings us to a sobering thought. If this is the best we can do, more than a century later, with all the technology we now have, what happens when the next Tunguska-class object decides not to spare a city? To see that, we have to move the blast forward in time, out of the swamps of 1908 and into our wired, crowded, fragile present. Imagine it's not 1908. It's next Tuesday. The same kind of object, tens of meters across, moving faster than a rifle bullet, slides into Earth's atmosphere. Same mass, same speed, same angle, same 10 or 20 megatons of energy. But this time, it doesn't pick a patch of swampy taiga and a few unlucky reindeer herders. It picks a city. The first difference is that we don't get silence. We get phones. Before the blast itself, there are the witnesses with modern eyes and modern cameras. People on their morning commute notice something strange low on the horizon. A bright point that shouldn't be there, moving too fast, leaving a thick, unnatural tail. Within seconds, somebody's recording it. Within another few seconds, it's on social media. If you've seen the Chelyabinsk videos from 2013, the blinding streak across the Russian winter sky, the flare that briefly outshines the sun, you've already watched a small-scale rehearsal. That was a 20-meter object, maybe half a megaton of energy. Tunguska was perhaps 20 to 40 times more powerful. Now scale that up and drop it over somewhere that actually shows up on a nighttime satellite image. If the airburst happens high enough, tens of kilometers up, the city might get away with just broken windows, some injuries, a terrifying light show, and a few minutes of pure panic as everyone tries to figure out whether this is a nuclear attack. If it happens at Tunguska altitudes, 5 to 10 kilometers above the ground, the story gets darker. Glass doesn't just crack, it becomes shrapnel. Unreinforced buildings near ground zero don't just shake. They lose walls, roofs, entire floors. People in the open are thrown to the ground, scorched by radiant heat, before the shockwave even arrives. In Tunguska, the blast knocked down trees out to 20 or 30 kilometers, swap trees for buildings, and you've drawn a ring of severe damage roughly the size of a major metropolitan area. Not vaporized, not cratered, but peeled open. Roads blocked, power lines gone, water mains severed, hospitals flooded with the injured just as their own windows shatter and their power flickers out. Downwind, fires start. In 1908, they burned through forest and peat. Today, they'd rip through suburbs and industrial belts, through fuel depots, chemical plants, high-rise towers with flammable interiors. Firefighting relies on infrastructure, water pressure, clear roads, functioning communication. All of that would be exactly what the shockwave just ruined. So yes, the physical damage would be worse, but in another way, the 21st century gives us something 1908 never had. A chance, however small, to see the intruder coming. Around the world, robotic telescopes are scanning the sky every clear night. Projects like Pan-STARRS, the Catalina Sky Survey Atlas, the Zwicky Transient Facility, they're all part of a global effort to map near-Earth objects, the asteroids and comets whose orbits cross ours. For the big ones, this system works surprisingly well. An object a kilometre across is bright enough that, with modern surveys, we can usually spot it years or decades before any close approach. Those giants move slowly across the starfield. They show up as faint, obvious streaks night after night. Their orbits can be measured and predicted. If something civilization-ending were on a collision course in the near future, there's a good chance we'd already know. But Tunguska wasn't a kilometre-class object. It was small enough to sneak. That's the awkward truth of planetary defence. The hardest threats to catch early are not the monsters that wipe out continents. They're the middleweights that can erase a city. A 50-metre, dark, stony asteroid doesn't reflect much sunlight. From tens of millions of kilometres away, it's a dim dot against a bright, cluttered backdrop. Our surveys are good, but they're not omniscient. They have blind spots in time and space. The sky overhead isn't being watched continuously from every location. Our telescopes can't see through clouds, or during daylight, or into the dazzling glare around the sun. That last part is especially important. Chelyabinsk came from the sunward direction. From a patch of sky our ground-based surveys effectively don't monitor. It arrived unannounced, no warning, no bulletin, no alert. Just a streak, a flash, and a shock wave that injured more than 1,000 people, mostly with flying glass. A Tunguska-class object coming from the same blind cone could do the same thing, just on a grander and much more lethal scale. Even when the geometry is kinder, discovery times can be brutally short. For a middle-sized asteroid, advance warning can mean a few days, sometimes a few hours. Sometimes, as with Chelyabinsk, negative. We reconstruct its orbit after the fact from dashcam videos and satellite sensors that noticed the flash. Space agencies know this. They're not complacent about it. NASA's Planetary Defense Coordination Office, ESA's Near-Earth Object Programs, independent surveys and proposed space-based infrared telescopes like NEO Surveyor, they're all in part a response to Tunguska and its modern echoes. The goal is simple to say and hard to achieve. Find them sooner, especially the small and medium ones. Space-based observatories would help because they can look out from above Earth's atmosphere, into wavelengths where dark rocks glow in infrared, and into solar-adjacent parts of the sky our ground telescopes have to avoid. With enough of these eyes, the silent middleweights become louder, their orbits pinned down years instead of days in advance. But we're not there yet. Right now, if another Tunguska-class object were on track for, say, a mid-latitude city 3 months from now, there's a non-zero chance we simply wouldn't know until it was almost on top of us. And that's where the grimly practical side of the story kicks in: emergency planning. Impact scientists have taken Tunguska, Chelyabinsk, and data from nuclear tests and turned them into maps, contour plots of overpressure, wind speed, thermal radiation as a function of distance and yield. They've used those to play what if with modern cities. What if a 15 megaton airburst happens at 8 kilometers altitude above downtown Los Angeles, above Beijing, above Sao Paulo? The details vary with local geography and building codes, but the broad findings are the same. First, indoors beats outdoors. The shockwave moves at hundreds of meters per second. If you see an insanely bright flash in the sky that makes deep shadows and lasts more than a second or two, your best move is counterintuitive. Look away, move away from windows, get behind something solid. You may have tens of seconds before the main blast front arrives. Second, glass is the silent enemy. In Chelyabinsk, most injuries came when people, curious and alarmed, walked to their windows to see what just lit up the sky. and were standing right there when the shock hit and turned those windows into knives. Public-facing safety advice now explicitly includes this lesson: don't crowd the glass. Third, vertical cities suffer differently than horizontal ones. High-rise buildings can shield streets from direct thermal radiation, but they also create canyons that channel and reflect the shock. Rooftop infrastructure, HVAC units, water tanks, antennas, turns into airborne debris. Emergency responders need to think in 3 dimensions: elevators out, stairwells blocked, roofs inaccessible. All of this is the kind of planning you can only really justify if you believe Tunguska-class events are part of Earth's future, not just its past, and the statistics say they are. Maybe not this decade, maybe not this century, but on timescales of civilization the dice will be rolled again, which brings us to a strange tension at the heart of the Tunguska story. On the one hand, our understanding of what happened in 1908 has never been better. We can model the blast, estimate the altitude, back-calculate the mass and speed range. We can tease extraterrestrial fingerprints out of century-old peat. We can watch, frame by frame, what a smaller cousin did to Chelyabinsk in 2013 and scale it to Tunguska energies. On the other hand, the culprit itself still refuses to line up neatly in the dock. Asteroid or comet? Stony body or something icier and more fragile? Single intruder or complicated breakup with multiple fragments? Different teams, different models, different weightings of the evidence come to slightly different conclusions. Those differences matter for planetary defense. A dense, stony asteroid and a fluffy cometary fragment of the same size don't behave the same way in our atmosphere. They break up at different heights, distribute their energy differently, pose different combinations of blast, heat, and possible ground impact. If we can't say with high confidence what Tunguska was, we can't be completely certain what the next one will be. So we live in this uneasy space. We know enough to run simulations, issue guidelines, design telescopes, and even sketch out missions that could, in principle, nudge a threatening asteroid off course decades before impact. But when we look back at that morning in 1908, deep in the Siberian forest, there's still a veil we can't lift. No crater we can point to and say, here. No definitive fragment we can raise and declare, this is the thing that flattened the world's largest forest in a single breath. We've turned Tunguska from an unthinkable bolt from the blue into a case study, a data point, a warning model. Yet the object itself remains a ghost. And as long as that ghost refuses to fully resolve, there's a quiet reminder hanging over every clear, ordinary morning sky. The next bright streak might come with days of warning, or it might just appear, without preamble, like it did over Siberia. A sudden, blinding question mark that only answers itself when the sky explodes. And that's really where Tunguska leaves us. For all the modelling, all the simulations, all the painstaking core samples of frozen peat and charcoal, the core of the story is still unresolved. We are almost certain about the how. A huge object, unnamed, unrecorded, never seen by a telescope, hit the upper atmosphere at cosmic speed. The air in front of it compressed and heated until the object itself began to break. At somewhere around 5 to 10 kilometers up, the strain reached a limit. The intruder tore itself apart in a fraction of a second, converting its orbital energy into a vast expanding fireball of superheated air. Shock waves raced outward and downward. A column of scorched wind punched toward the ground. Trees, rooted for centuries, were snapped like matchsticks and thrown flat. Over 2,000 square kilometers of forest were knocked over as if a gigantic invisible hand had brushed them aside. We know this because the pattern on the ground doesn't lie. The fallen trees point away from a central zone of near-total devastation. Trunks stripped of branches, stumps blasted bare, a ring of radial flattening that matches what you'd expect from an airburst, not a surface impact. There is no central pit, no raised rim, no ejector blanket. Just a scorched centre and a neatly organised chaos all around it. Seismographs, barographs, eyewitness accounts of light and sound at staggering distances, all of them converge on the same basic story. Something exploded in the air above Tunguska with a yield in the low tens of megatons. More powerful than any human-made bomb until the mid-20th century. Over in seconds. Gone forever. So the mechanism, an atmospheric explosion, isn't really the argument anymore. The argument is over what sacrificed itself to make that fireball. The chemical traces we've found in soils and tree resin, tiny spherules rich in nickel and other metals, dust with an extraterrestrial signature, tell us that the intruder wasn't just air. It was some kind of space rock, but that still leaves a big fork in the road. If it was a dense, stony asteroid, something like the smaller Chelyabinsk object scaled up, then it might have been 50, 60, maybe 80 meters across, with enough strength to punch deep into the atmosphere before catastrophically failing. That fits some blast models nicely. It also lines up with what we've seen from more recent small asteroids that shatter in the sky. But there are details that make some researchers pause. The apparent altitude of maximum energy release, the wide area over which eyewitnesses described unusually bright night skies, the lack of any confirmed fragments on the ground, despite a century of searching, the peculiar chemistry of some of those microspheres. Put together, those hints start to look friendlier to another suspect, a fragile, volatile-rich cometary body. A chunk of comet, more ice and dust than solid rock, would enter the atmosphere differently. Lower density, lower strength, earlier breakup, more complex distribution of energy. Some models suggest that a relatively small, fluffy body could still create Tunguska-scale damage by disintegrating higher but more gradually, spreading devastation over a wider footprint. Then there are hybrid ideas. Stony core with a comet-like mantle, a rubble pile held together by gravity and weak forces, maybe even a small fragment from a larger long-period comet that had been shedding debris for millennia. Every new simulation introduces another nuance: fragmentation into multiple pieces, angled shock fronts, interactions with atmospheric layers we're only now starting to model with supercomputers. And that's why, after more than 100 years, you can still find impact scientists politely arguing in conference halls and research papers. Same blast, same cracked trees. Two main suspects. The asteroid camp points to the metallic spherules, the absence of obvious cometary signatures in the chemistry, the resemblance to known asteroidal events. The comet camp leans on eyewitness reports of luminous skies, possible long-distance dust effects, the way some models of a more fragile body seem to recreate the observed damage pattern better. Both sides are pulling on the same handful of threads, trying to reconstruct an object that disintegrated completely over a lonely river in Siberia at a time when no one had a camera, no one had a satellite, no one even knew they should be paying attention. So the mystery that still stands is not whether nature can do this. We've seen it. We watched Chelyabinsk arrive, detonate, and vanish in a million dashboard reflections. We've mapped ancient impact sites on every continent. We know in a way the people of 1908 did not that the sky is full of slow, cold bullets whose orbits sometimes cross our own. The mystery is which bullet exactly tore through that patch of sky on that particular morning, and what that implies for the dice we're rolling in the future. If Tunguska was a stony asteroid, then it's part of a population we're already mapping, near-Earth objects that loop around the Sun on orbits not too different from our own. Hard to see when they're small and dark, but at least conceptually familiar. If it was a fragment of a long-period comet, that's a different story. Those come screaming in from the deep freeze of the outer solar system on elongated paths that may only bring them near us once in tens of thousands of years. They can arrive fast, from steep angles, out of poorly surveyed regions of space, giving us less warning and fewer options. Either way, the lesson is the same, and it's not subtle. In a handful of seconds, without touching the ground, a natural object can rewrite a landscape the size of a small country. It can turn a living forest into a vast flattened diagram of shock physics. It can take a quiet morning and with no more malice than a falling raindrop, draw a circle of devastation on the map that will echo through science, folklore and planetary defense policy for centuries. The Earth feels solid when we stand on it, stable, permanent. Tunguska is the reminder that sometimes all it takes is one stone, or one ball of ice and dust, arriving at the wrong angle, on the wrong day, to prove otherwise. So I'm curious, knowing what you know now, what's your theory? Stony asteroid, fragile comet, weird hybrid, something even stranger. If you had to place a bet on the thing that flattened 80 million trees in seconds, where would you put it? Let me know in the comments, and while you're down there, tell me where you're listening from. One of the joys of making these deep-time, deep-space stories is knowing they're being heard all over the planet that's at the centre of them. If you found this journey through Tunguska's mystery compelling, it really helps the channel if you like the video. Leave a comment with your thoughts or questions, and subscribe so you don't miss what comes next. That simple trio, like comment, subscribe, does more than you might think to tell the algorithm that these long, strange stories are worth sharing. And if you'd like to go even further down the rabbit hole of Earth's forgotten catastrophes and hidden turning points, I've put together a book of prehistoric secrets, stories of bottlenecks and near extinctions, lost worlds and unlikely survivals. It's written in the same slow-burn narrative style as this episode, and you can find it at sleepytimehistory.com. Wherever you are, under clear skies, under clouds, on a quiet morning that feels safe and ordinary, remember that somewhere up there, the next Tunguska-class visitor is tracing its path around the sun. We don't know its name yet. We don't know when or where it will arrive. But we do know this. When the sky finally asks us that question again, the answer will depend on whether we've learned enough from the mystery that still stands over a lonely patch of Siberian forest, where the trees still remember the day the air itself came down.